Good morning everyone, good morning. I welcome you all again to NEET Elite. I hope you guys are doing great, having the good time. So people, you can let me know first of all in the chat box if I'm audible and visible to everyone. Good morning Chitra, hello Faisal, hi Srinidhi, hello Rakesh, hello Vishal, welcome back, hello Amrita, hello Gayatri, welcome back people, welcome back, good morning, hi Karthik. Yeah, I'm seeing you guys after so long, yeah, right? So people, as you all must be knowing, on Sunday we were supposed to have a session of 10 hours, but that is postponed to tomorrow. So tomorrow at the same time, 9 a.m. in the morning, we'll be taking a session in which we'll be revising the whole chemistry in the form of some 1100 questions, right? Okay, so be there on time for the tomorrow session, right? So just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys. Just let me know in the chat box. Just let me know people in the chat box if I'm audible and visible to you guys. Welcome back everyone, welcome back. So as you all must be knowing, today we are going to do the complete chemistry formula revision, right? Whatever formulas are there in your chemistry, we are going to revise those formulas, right? And at the end, I'll be giving you the PDF of the whole session as well in the Telegram group, right? And you can revise it there at the same time, okay? So before starting the session, the ones who are new to the channel, let me introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher writer on this NEET Elite channel, right? The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this NEET Elite channel, yeah? So do like the video, share the video with your friends, and do subscribe to the channel as well, okay? Perfect. Dinesh, the Telegram link is there in the description box of the video. You can click it afterwards, you can get added to the Telegram group, right? Okay. Alright, so let's get going then with the NEET 2021 complete chemistry formula revision with the first chapter. That's something which we call as mole concept, right? Let's see what all formulas we have got in the chapter mole concept, and I'm sure it's going to be helpful for you to revise all the formulas, right? So let's get going then. Let's get started with the today's session. Okay, in the mole concept chapter, let's start with the basic formula. Well people, let me tell you, we have got three basic formulas to calculate number of moles of a particular substance, right? Okay. The first formula to calculate number of moles, I'm writing it over here. Number of moles, which I represent by N, that's always equal to given mass of the substance, that's always equal to given mass of the substance in grams divided by molar mass of the substance. This is the first basic formula by means of which we can calculate number of moles. Point number one. Number two, the second formula to calculate number of moles, what is that going to be? That is equal to given number of particles divided by Avogadro's number, and the value of Avogadro's number, as you all must be knowing, that is 6.022 into 10 raised to the power 23, right? This is the second formula by means of which we can calculate number of moles of a particular substance, right? The third formula to calculate number of moles, let me tell you that third formula is only valid for gases present at STP, okay? So I'm writing number of moles of a gas present at STP. What it's going to be? It's simply going to be given volume of the gas in liters divided by 22.4 liters, right? Or you can write it as given volume of the gas in milliliters divided by 22400 milliliters, right? These are the three basic formulas by means of which we can calculate number of moles of a particular substance. Whenever we are given with the mass of the substance, divide the given mass of the substance by its respective molar mass, you'll be getting the number of moles, right? Second formula, whenever you'll be given with the number of particles of the substance, you're supposed to divide the number of particles by the Avogadro's number. You'll be again getting the number of moles. The third formula, it's only valid for gases present in STP. That's going to be given volume of the gas in liters divided by 22.4 liters, or you can say given volume of the gas in milliliters divided by 22400 milliliters. These are three basic formulas by means of which we can calculate number of moles. Yeah. Next, let's move on to the next part. Well, people, let's assume I have got the element X, right? Let's assume I have got the element X. Let's assume this element has got three different isotopes. Let's assume this element has got three different isotopes. What are isotopes all about? Isotopes are the atoms of the same element having same atomic number, which I'm representing by Z, but different mass numbers, which is M1, M2, and M3, right? Let's say these are the three different isotopes of a particular element X, right? As you all must be knowing, whenever the element exists in the form of isotopic forms, at that time we calculate average atomic mass for the element, which is denoted as MAV, right? And in order to calculate average atomic mass of the element which exists in the form of isotopes, we definitely need the percentage abundances of these isotopes, right? Let's assume the percentage abundances of these isotopes are represented by A, B, and C. A, B, and C, these are first of all the percentage abundances of these isotopes of this particular element, right? So remember, whenever the element exists in the form of isotopes, at that time we calculate average atomic mass of the element, which is calculated by the formula M1 multiplied by A plus M2 multiplied by B plus M3 multiplied by C dash 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 plus how many isotopes will be there, right? Divided by A plus B plus C plus dash dash like this, right? This is the simplest formula by means of which you can calculate the average atomic mass of the element which exists in the form of different isotopes, right? Remember, at the same time, take a note of one thing. The sum of percentage abundances, the sum of percentage abundances of all the isotopes of a particular element is always equal to 100, right? Do remember this point as well. Well, first of all, let me tell you, this is the formula by means of which we can calculate the average atomic mass of the element which exists in the form of different isotopes, right? It's going to be M1 multiplied by A, where A stands for the percentage abundance of this isotopes, B stands for percentage abundance of this isotope, and C stands for percentage abundance of this isotope as well, right? I'm sure this is clear to everyone, yeah? Sir, the video is buffering. People, am I perfectly audible and visible to everyone? You can just let me know in the chat box. Just let me know in the chat box. Hello Arshad, yes, I'm seeing you guys after so long. Yeah? Just give me some confirmation if I'm audible and visible to you guys properly. Perfect. Alright, so this was the second formula by means of which we can calculate average atomic mass of the element which exists in the form of isotopes. Okay? Let's move on to the third point. What is that going to be? Have a look. Have a look, guys. Understand properly. The third point is for, the third formula is for average molar mass of a gaseous mixture. Average molar mass of a gaseous mixture. How do we calculate the average molar mass of the gaseous mixture? Understand properly. Yeah? Okay. See guys, for example, this is the container which I'm taking. Let's assume this is the container which I have, and in this container I have got three chemically non-reacting gases, gas 1, gas 2, and gas 3. These are the three gases present in the container. That means currently in the container I have got a mixture of gas. I have got a gaseous mixture present in the container, right? Let's assume mass of gas 1 in the container is represented by W1 grams, mass of gas 2 in the container is represented by W2 grams, and mass of gas 3 in the container I'm representing by W3 grams, right? Let's assume number of moles of gas 1 in the container is equal to N1, number of moles of gas 2 in the container is equal to N2, number of moles of gas 3 in the container is equal to N3, right? Let's assume the mole fraction of gas 1 in the container I'm representing by Chi1, mole fraction of gas 2, Chi2, mole fraction of gas 3 I'm representing by Chi3, right? Let's assume molar mass of gas 1 I'm representing by M1, molar mass of gas 2 M2, molar mass of gas 3 I'm representing by M3, right? So basically, I have got a gaseous mixture in the container and I need to calculate the average molar mass of this gaseous mixture. There are certain formulas by means of which you can calculate the average molar mass of this gaseous mixture. Formula number 1. Average molar mass of the gaseous mixture, that is simply going to be equal to mass of the mixture divided by number of moles present in the mixture. And what is going to be the mass of this complete mixture? It's going to be W1 plus W2 plus W3 divided by number of moles present in the mixture is going to be N1 plus N2 plus N3. This is the first formula by means of which you can calculate average molar mass of this gaseous mixture, right? First formula. Second formula to calculate the average molar mass of the gaseous mixture. That's going to be equal to M1 N1 plus M2 N2 plus M3 N3 plus dash dash divided by what? Divided by N1 plus N2 plus N3. This is one more formula by means of which you can calculate the average molar mass of the gaseous mixture, right? Let's move on to the third formula. Before giving the third formula, let me tell you the third formula which I'm going to give you now, that is valid only when the mixture is present at constant pressure and temperature. When the pressure and temperature of the mixture is kept constant, is kept fixed, at that time only we can use the third formula to calculate the average molar mass of the gaseous mixture. And what is the third formula? It's going to be M1 V1 plus M2 V2 plus M3 V3 divided by what? Divided by V1 plus V2 plus V3. This formula is only valid when the gaseous mixture is present at constant pressure and temperature, right? When the pressure and temperature of the mixture does not change, at that time, the average molar mass of the mixture is calculated by this formula, right? This is the third formula. Talking about the next formula. Average molar mass of the mixture can be calculated like this as well. M1 Chi1 plus M2 multiplied by Chi2 plus M3 multiplied by Chi3. This is one more formula by means of which you can calculate the average molar mass of the gaseous mixture. So people, I want you guys to remember these four formulas by means of which you can calculate the average molar mass of the gaseous mixture. I'm sure it's clear to everyone, right? Okay? Right people? Every single thing is clear till here? Jagan, that 10 plus hour session is done tomorrow. That will be done tomorrow, right? Tomorrow at the same time, 9 a.m. in the morning, I'm starting the session. Okay? Perfect. Perfect. I'm sure till here it's clear to everyone. Okay? Let's move on to something called as percentage of an element in a given compound. Percentage of the element in a given compound is always equal. This is one more formula, okay? Percentage of an element in a given compound is always equal to mass of the element in the given compound divided by molar mass of the compound multiplied by 100. This is one more formula by means of which you can calculate the percentage of an element in a given compound. For example, I'm giving you example as well. Let's say I've got glucose, right? Let's say I've got 1 mole of glucose, C6H12O6. For example, I need to calculate the percentage of carbon in this glucose, percentage of hydrogen in this glucose, percentage of oxygen in this glucose. And how do we do this? See guys, I'll be simply writing percentage of carbon in glucose is equal. It's going to be mass of carbon in 1 mole of glucose, which is going to be 6 multiplied by molar mass of carbon is 12, divided by molar mass of the compound, that is 180 multiplied by 100. Solve this, get the percentage of carbon in the compound, in the glucose. Similarly, you can calculate the percentage of hydrogen in glucose as well. It's going to be equal to 12 multiplied by molar mass of hydrogen is 1 gram divided by molar mass of compound, as you all must be knowing, that's 180 grams per mole multiplied by 100. Solve this, get the percentage of hydrogen in glucose. Similarly, you can calculate the percentage of oxygen in glucose as well, which is going to be 6 multiplied by 16 divided by 180 multiplied by 100. That's how you calculate the percentage of oxygen in glucose. I'm sure this formula is clear to everyone, right? Okay, from this formula, question can be directly asked. Yeah? Moving on to certain more formulas. There is one formula to calculate percentage yield of the reaction. I'm sure you all must have heard about this percentage yield. How do we calculate percentage yield? Percentage yield is calculated by the formula experimental amount divided by expected amount multiplied by 100. This is the formula by means of which you can calculate percentage yield of a particular reaction, right? Let me tell you, this expected amount you'll be always calculating by using the stoichiometry of the reaction, right? Which we have discussed in the actual sessions as well. This expected amount you can calculate by using the stoichiometry of the reaction, right? And most of the times, this experimental amount will be always given to you in the question, most of the times, right? Similarly, we have got one more formula by means of which we can calculate percentage purity. How do we calculate percentage purity? It has got the simple formula. Percentage purity of a compound is equal to mass of pure compound divided by mass of impure sample divided by mass of impure sample multiplied by 100. This is one more formula by means of which you can calculate percentage purity of a particular compound in a given impure sample, right? You will be given the impure sample, and in the impure sample you will be supposed to calculate the percentage purity of a compound, and this is the formula by means of which you can calculate percentage purity, right? Okay, perfect. Absolutely, right? So these were formula related to percentage yield and percentage purity, right? People, there is one more thing. You might have heard something about the limiting reagent. How do we identify which one is the limiting reagent? How do we identify which reactant is the limiting reagent among all? Yeah? For example, let's say I've got the balanced chemical equation as N1A plus N2B. It gives N3C plus N4B. Let's assume this is a balanced chemical equation. This N1, N2, N3 and N4, these are the stoichiometric coefficients of A, B, C and D respectively, right? Now we will have a look. Let's assume at time t is equal to 0, initially the number of moles of A which are given to me, that's X, number of moles of B which are given to me, that's Y. This will be 0, this will be 0 because the reaction has not started yet. I'm talking at time t is equal to 0. Let's assume at time t is equal to 0, I've got some X moles of A, I've got some Y moles of B. Now I need to identify among A and B, which one is the limiting reagent. How do we do that? How do we check that? What you simply are going to do is divide the given moles of the reactants by their respective stoichiometric coefficients. So you'll be dividing this X with the stoichiometric coefficient N1, you'll be dividing this Y with the stoichiometric coefficient N2, right? Okay. The value which comes out be lesser among the two. These will be two values which I'll be getting, right? X divided by N1, I'll be getting some value. Y divided by N2, I'll be getting some value. The value which is going to be lesser. Let's assume this X divided by N1 is less than Y divided by N2. If X divided by N1 is less than Y divided by N2, that actually means A is going to be your limiting reagent, right? That reactant for which this value comes out to be lesser, that is absolutely going to be always your limiting reagent. If this is the limiting reagent, that means this B is going to be your excess reagent. This is the simple way by means of which you can check The simplest way by means of which you can check which one is the limiting reagent in the given chemical reaction. Divide the given number of moles by their respective stoichiometric coefficients. For the reactant whose value comes out to be less, that's always going to be your limiting reagent. I'm sure this again clear to you, right? Okay. Yes, tomorrow I'll be doing that 10+hour session. Yes, tomorrow. That's going to be perfect NEET level MCQs, right? Perfect NEET level MCQs it's going to be, right? Okay, so this was about the limiting reagent. Now let's move on to something called as concentration terms, right? Let's move on to something called as concentration terms. Have a look, guys. Before going to the formulas of the concentration terms, I need to tell you few basic things. What are those basic things? Have a look. Let's say I've got a solution. Let's say this is the container in which I've got a solution. This solution absolutely will have two components, as you all must be knowing. There'll be two components of this solution, right? One is going to be solute, one is going to be solvent. Remember, solute I'll be representing by number 2, solvent I'll be representing by number 1, right? W stands for mass. W stands for mass of the substance in grams. M stands for molar mass of the substance in, right? Molar mass of the substance. N stands for number of moles of the substance, as you all must be knowing, right? Number of moles of the substance. And at the same time, E stands for equivalent mass of the substance. Equivalent mass of the substance, right? Now there are some formulas which you need to remember. What are those formulas going to be? Karthik, I'm not going to give any sort of questions in the today's session. I'm not going to give any sort of examples. It is just the formula revision, right? Questions will be done in tomorrow's session, right? And tomorrow we are going to do 1000+ questions from your chemistry part, okay? So we will have a look. The first formula, which is weight by weight percent of solute, or you call it as the mass percent of the solute. Or you call it as the mass percent of solute. How do we calculate weight by weight percent of solute or mass percent of the solute? Have a look, guys. There is a simple formula for it. It's going to be mass of solute, which I represent by W2, mass of solute in grams, divided by mass of solution in grams, multiplied by 100. This is the first formula by means of which you can calculate weight by weight percent of solute. Similarly, if you want to calculate weight by weight percent of solvent, that's going to be equal to 100 minus weight by weight percent of solute. As simple as that, right? Okay. This is the first formula. The second one, that is valid for weight divided by volume percent of solute. How do we calculate weight by volume percent of solute? As you all must be knowing, weight divided by volume percent of solute is equal to mass of solute in grams divided by volume of solution in milliliters multiplied by 100. This is the formula by means of which we can calculate weight by volume percent of solute, right? Now people, there is a simple relation between weight by weight percent of solute and weight by volume percent of solute. What is that relation going to be? Let me tell you. Weight by volume percent of solute, which I'm representing by 2, weight by volume percent of solute is always equal to weight by weight percent of solute multiplied by density of solution. This is the direct result between weight by weight percent of solute and weight by volume percent of solute, right? Okay. Arshad, remember, solute you are going to represent always by 2, solvent you will be representing always by 1. That's it. That's all, right? Okay, just give me a second. So let's move on to the next formula. Let's move on to the next formula, which is used to calculate volume by volume percent of solute. How do we calculate volume by volume percent of solute? It's simply going to be equal to volume of solute in milliliters divided by volume of solution in milliliters multiplied by 100. This is the formula by means of which you can calculate volume by volume percent of solute, right? Now people, talking about the next part, that's going to be equal to mole fraction of solute. Mole fraction of solute is simply going to be equal to number of moles of solute in the solution divided by total moles present in the solution, which is going to be N1 plus N2. Similarly, you can calculate mole fraction of solvent, which I'm representing by Chi1, which is given as number of moles of solvent divided by total moles present in the solution, which is N1 plus N2, right? And remember always, for a binary solution, chi1 plus chi2 is always equal to 1. I'm sure you all must have heard about this as well, right? Okay, I'm sure it's clear. Right, people? Moving on to few more formulas. These were weight by weight, weight by volume, volume by volume, and mole fraction. Moving on to something called as molarity. Molarity of the solution, which we represent with capital M. Molarity of the solution. Molarity of the solution is defined as number of moles of solute divided by volume of solution in liters. This is the first formula by means of which we can calculate molarity of the solution. Or you can write it like this as well. Mass of solute in grams divided by molar mass of solute multiplied by volume of solution in milliliters multiplied by 1000. This is one more formula by means of which you can calculate molarity, right? Number of moles of solute divided by volume of solution in liters, or you can say mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by volume of solution in milliliters. And as you all must be knowing, molarity is molarity is temperature dependent, right? This is something which you all must be knowing. Molarity is temperature dependent. Okay. Now people, one more formula to calculate molarity, one direct result I'm giving you. That's going to be 10 multiplied by density of solution multiplied by weight percent of solute divided by molar mass of solute, which I'm representing by M2. This is one more formula by means of which you can calculate molarity of the solution. As simple as that. Okay? Right, people? So these are the formulas by means of which you can calculate molarity of a particular solution. Now comes one more, that's called as molality. And molality, as you all must be knowing, that is denoted by small m, right? The first formula to calculate molality, that's going to be number of moles of solute divided by mass of solvent, which I'm representing by W1 in kilograms. First formula to calculate molality. Similarly, I can convert it as mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams. This is one more formula by means of which you can calculate molality, right? Now people, all of you must be knowing one relation, that is the relation between molarity and molality, right? What is the relation between molarity and molality? Let me tell you, molality, that's always equal to 1000 multiplied by molarity of the solution divided by 1000 multiplied by density of solution minus molarity of the solution multiplied by molar mass of solute. This is one direct result by means of which you can relate your molality with molarity, right? This is the result by means of which you can relate molality with molarity, right? There is one more direct result which I want you guys to remember. What is that going to be? Molality is always equal to chi2, which is the mole fraction of solute, multiplied by 1000 divided by 1 minus chi2 multiplied by M1. M1 stands for molar mass of the solvent, right? This is the result between molality and the mole fraction. I'm sure you're going to remember this one as well from now onwards, okay? People, you can directly remember these results. You can solve the equations in a very lesser time if you remember these direct results. For example, this result. For example, this result. For example, this result. Remember these relations directly, okay? Perfect. Moving on to a few more. There is something called as parts per million of solute. How do we calculate ppm of solute? Simple. Parts per million of solute is equal to mass of solute in grams divided by mass of solution in grams multiplied by 10 raised power 6. This is one more result. This is the way to calculate parts per million of solute. Similarly, if I talk about parts per billion of solute is equal to mass of solute in grams divided by mass of solution in grams multiplied by 10 raised to the power 9. 10 raised to the power 9, okay? Or you can write it like this as well. You can say parts per million of solute is equal to weight by weight percent of solute multiplied by 10 raised to the power 4, right? Similarly, you can say parts per billion of solute is equal to weight by weight percent of solute divided by, multiplied by what? Multiplied by 10 raised to the power 7, right? These are the results which I want you guys to remember from now onwards, correct? Right, people? Okay. There is one more thing. There is one more thing. That's what we call a strength. That's what we call a strength, which is measured in grams per liter. Which is measured in grams per liter. It's simply going to be equal to mass of solute in grams divided by volume of solution in liters, right? This is one more result by means of which you can calculate strength. I'm sure you're going to remember this from now onwards as well. Okay? Right, people? So these were the formulas related to the mole concept, right? You're just going to remember these relations, and majority of the times whenever questions comes from the mole concept, it comes from concentration terms, right? And in the concentration terms, these are the direct result, these are the formulas which I want all of you to remember. People, is it clear to everyone? Should I be moving ahead? Just let me know in the chat box. Is everything clear till here? Right? Perfect. Perfect, guys. Just a second. This is the diagram which every one of you must be knowing, right? How do we convert moles into volume, moles into mass, moles into particles, particles into moles, and so on. Very simple result this is going to be, right? Remember, whenever the question comes, like whenever you are supposed to calculate the number of electrons, protons, or neutrons, how do we do that? There comes a particular question, calculate the total number of electrons, protons, neutrons, and so on. You need to follow this block diagram for that. Whatever is the given quantity that's given in the question, convert the given quantity to number of moles, convert the moles into molecules. From molecules you can calculate atoms. From atoms you can calculate electrons, protons, neutrons. This is the simple block diagram which its application I've shown you in the actual sessions, in the long-term sessions as well, if you remember, right? Okay, just remember this in order to calculate electron, protons, neutrons, right? I've already given this diagram if you remember. Okay, average molar mass of the mixture. This is something which we have discussed, right? Just give me a second. Percentage yield of the reaction. This is something which we have discussed too, right? This is something which we have discussed too. Percentage purity we have discussed. Concentration terms starting with mass percent or weight by weight percent, then weight by volume, then volume by volume, right? Molarity, its results, molality, right? Mole fraction, relation between molarity and mole fraction, this is discussed. Relation between molality and molarity, this is also discussed. Ppm of solute, it's also discussed. Parts per billion of solute, that's also discussed, right? Okay, let's move on to a few results from the chapter Redox Reactions, okay? I'm sure everything is clear till here, yeah? Right, people? Okay? Perfect. So first of all, in the Redox reaction chapter, what all things we need to discuss? What all formulas we need to remember? First of all, let's see how do we calculate equivalent mass of the substance. Equivalent mass of the substance. Remember, it's always equal to molar mass of the substance divided by n factor of the substance, or n factor you can call it as valency factor as well, right? A simple result which every one of you must be remembering. Equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the same substance, right? Now the point is, how do we calculate n factor of different substances, okay? Let me start with the elements. Remember, for an element, n factor is always equal to the valency of it, right? For an element, n factor of it is always equal to valency of it. Point number one. If I'll be having an ion, for an ion, n factor of it is equal to magnitude of charge present on the ion. Magnitude of charge present on the ion, right? Moving on to the third one, that's going to be n factor of the salt. How do we calculate n factor of the salt? N factor of the salt is basically equal to LCM of charge present on cation, LCM of charge present on cation and charge present on anion. Okay, this is the way by means of which we can calculate n factor of a salt. Similarly, n factor of an acid. N factor of the acid is always equal to the basicity of the acid. And how do we define the basicity of the acid? It's equal to the number of replaceable H positive ions. The number of replaceable H positive ions, right? Okay. Similarly, n factor of a base. N factor of a base, as you all must be knowing, that's basically equal to acidity of the base. And what is acidity all about? Acidity is defined in many ways. Number one, number of OH negatives, number of replaceable OH negatives, or number of OH negatives of base donates. Or you can say number of H positives it accepts. Number of H positives it accepts. Right? This is by means of which we can calculate, this is the formula by means of which we can calculate n factor of the base, n factor of acid, n factor of salt, n factor of ion, n factor of element, in short, right? Similarly, guys, remember few more important things. What are those important things? That's going to be n factor of an oxidizing agent or reducing agent. How do we calculate n factor of the oxidizing or reducing agent? It is equal to mod of change in the oxidation state. Mode of change in the oxidation state. For example, I'm giving you one example over here. Let's say I've got KMnO4. As you all must be knowing, KMnO4 in acidic medium, it gets converted into Mn di positive. If I'll ask you, what is the oxidation state of manganese over here? You'll say +7. What is the oxidation state of manganese over here? You'll say +2. So this is the initial oxidation state of manganese, this is the final oxidation state of manganese, right? So in order to calculate the n factor of KMnO4, you'll be calculating the change in the oxidation state of manganese, which is going to be equal to final oxidation state of manganese, which is +2, minus initial oxidation state of manganese, which is +7, right? And finally, you'll be getting the value over here as 5. So 5 is something which I call as n factor of KMnO4, right? As simple as that. Right, people? Similarly, if you talk about K2Cr2O7, K2Cr2O7 in acidic medium, it gets converted into Cr tripositive, sorry. What is the oxidation state of chromium? Right here, it's +6. Oxidation state of chromium, right here, it's +3. If you need to calculate the n factor of K2Cr2O7, you'll be simply calculating the change in oxidation state, which is final minus initial. Final oxidation state is +3 minus initial oxidation state is +6. The value comes out to be 3. But remember, this 3 is the change in the oxidation state for one atom of chromium, but I have 2 atoms, so I'll be multiplying this with 2. The value comes out to be 6. As simple as that, right? In short, how do we calculate the n factor of the substance which undergoes oxidation or reduction? Simply, you need to calculate the magnitude of change in the oxidation state of the element which undergoes the change, right? Okay, simple. Now after this guys, let me tell you a few more interesting things. Let's assume I've got a substance. Let's say I've got a substance in a chemical reaction, right? In which oxidation state of more than one element, either increases or decreases. Either increases or decreases simultaneously. Let's say I've got the substance, okay? I've got any substance in which oxidation state of, for example, more than one element either increases simultaneously or decreases simultaneously. How do we calculate n factor for them? It's simply going to be equal to mod of n1 plus n2 plus dash dash dash, right? Okay, for example, I'm giving you one common example. Let's say I have got FeC2O4. This is something which we call as ferrous oxalate, right? FeC2O4. Let's assume this FeC2O4, it gets converted into Fe tripositive plus carbon dioxide. Let's say this is the reaction which I have, right? First of all, if you calculate the oxidation state of iron right here, it's going to be +2. The oxidation state of iron right here is going to be +3. The oxidation state of carbon over here is going to be +3. The oxidation state of carbon over here is going to be +4, right? As you can see, the oxidation state of iron is changing, it's increasing, and at the same time, the oxidation state of carbon is also increasing. So this ferrous oxalate, it's a compound in which oxidation states of two elements are increasing simultaneously. And whenever you'll be having any substance in which the oxidation state of more than one element increases or decreases simultaneously, how do we calculate n factor of it? Simple, N1 plus N2. What is going to be N1? N1 is going to be the change in the oxidation state of iron right here, which I'll be representing by N1. Similarly, N2 is going to be change in the oxidation state of carbon, which I'm representing by N2. How do we calculate N1? N1, change in the oxidation state of iron. Final oxidation state of iron minus initial oxidation state of iron. Final 3, initial 2. 3 minus 2 comes out to be 1. So N1 value is 1. Similarly, what is N2? Plus 3 to plus 4. Change in the oxidation state. Final minus initial. 4 minus 3 comes out to be 1. But that 1 is the change in the oxidation state for one atom of carbon, but now 2. So N2 comes out to be 2. So you got N1, you got N2. Just add them up. Get the overall N factor of this ferrous oxalate over here. It is simply going to be equal to 2 plus 1, that is 3, right? I'm sure it's again clear to everyone, okay? Yeah? Perfect, people? Okay, so remember, whenever you'll be having a substance in which oxidation state of more than one element either increases or decreases simultaneously, at that time, this is how you calculate its N factor, okay? Perfect? Similarly, remember one more. Let's assume you have got a substance. Let's assume you have got a substance in which oxidation state of one element increases and another element decreases simultaneously, right? Let's say I've got a substance in which you have got different elements, right? Let's assume oxidation state of one element increases and other one decreases simultaneously, okay? How do we calculate N factor of that substance? N factor of that substance is calculated as mod of N1 minus N2, right? Just take the difference between the two. Okay, this is the formula by means of which you can calculate N factor of the substance in which oxidation state of one element increases and another one decreases simultaneously, right? Okay. Now people, there is something about the disproportionation reactions, right? How do we calculate the N factor of the substances which undergoes disproportionation? N factor of the substances which undergoes disproportionation. For example, I've got the reaction as Br2. It gives Br negative plus BrO3 negative. This is the reaction, for example, which I have, okay? Right? Have a look. What is the oxidation state of bromine right here? It's 0. Oxidation state of bromine right here is -1. Oxidation state of Br right here is going to be +5, right? See guys, understand properly. 0 to -1, oxidation state of bromine is decreasing, that means reduction is happening. Similarly, 0 to +5, oxidation state is increasing, that means oxidation is happening, right? So I simply say this Br2 is simultaneously undergoing reduction and oxidation. So I'll say Br2 is undergoing disproportionation. Br2 is undergoing disproportionation. And how do we calculate N factor of the substance which undergoes disproportionation? Let me tell you, N factor of substance which undergoes disproportionation is going to be equal to N1 multiplied by N2 divided by N1 plus N2. This is the formula which I want you guys to remember in order to calculate N factor of the substance which undergoes disproportionation, right? This is N1 and this is N2, and N1, N2, you already know how do we calculate it, right? Okay. Now people, one more last thing about the N factor calculation. What is that going to be? Whenever you'll be given with a balanced chemical equation, let's say I'm given with a balanced chemical equation. Understand? For example, the reaction is like this. Let's say I've got the reaction as 2 times A plus 3 times B plus 12 electrons. It gives 4 times C plus 6 times D. Let's say this is one balanced chemical equation which we have, okay? If I'll ask you how many total electrons are exchanged in the net reaction, 12 electrons have been exchanged in the net reaction, right? If I want you guys to calculate the n factor of A, you'll be simply saying n factor of A is equal to total electrons exchanged, that's 12, divided by stoichiometric coefficient of A, that's 2. So 12 by 2 comes out to be 6. If I'll ask you guys to calculate n factor of B, n factor of B is going to be equal to, again, total electron exchange, that's 12, divided by stoichiometric coefficient of B, that's 3. So 12 divided by 3 comes out to be 4. Similarly, n factor of C is going to be equal to total electrons exchanged, that's 12, divided by stoichiometric coefficient, that's 4. 12 by 4 comes out to be 3. Similarly, n factor of D is going to be 12 by 6, that comes out to be 2, right? So in short, what I want you guys to remember, whenever you're supposed to calculate the n factor of any reactant or product in a balanced chemical equation, what you simply are going to do, total moles of electrons exchanged divided by stoichiometric coefficients of either reactant or product, right? Depends on for which reactant or product you are supposed to calculate it. I'm sure this has been clear to everyone, right? Okay. For example, I've got the reaction as 2 times H positive plus 2 electrons, it gives H2. Let's say this is one reaction. It's a balanced chemical equation, right? I need to calculate n factor of this H positive. N factor of this H positive is going to be equal to total moles of electrons exchanged, that's 2, divided by stoichiometric coefficient of H positive, that's 2. 2 by 2 comes out to be 1. Let's assume I'm supposed to calculate the n factor of this H2. So you'll write n factor of H2 is equal to total moles of electrons exchanged, that's 2, divided by stoichiometric coefficient of H2, that's 1. 2 divided by 1 comes out to be 2, right? This is how you calculate n factor of different reactants or products if you are given with a balanced chemical equation. I'm sure this is again clear to everyone, right? Okay, this was about the n factors, which is very important, okay? Now, there is something called as normality, or before normality, there is something called as number of gram equivalents. How do we calculate number of gram equivalents of the substance? How do we calculate number of gram equivalents of the substance? Let me tell you, number of gram equivalents of the substance is always equal to mass of the substance in grams divided by equivalent mass of the substance. This is the first formula by means of which we can calculate number of gram equivalents of a particular substance, right? Mass of the substance in grams divided by equivalent mass of the substance, right? First formula. The second formula to calculate it is going to be number of moles of the substance multiplied by n factor of the same substance. This is one more result by means of which you can calculate number of gram equivalents, right? Similarly, the third one, that's going to be equal to normality of the solution multiplied by volume of solution in liters, right? This is one more result by means of which you can calculate number of gram equivalents. These are the three formulas which I want you guys to remember. Similarly, talking about the number of milli equivalents. Talking about the number of milli equivalents of the substance. In order to calculate the number of milli equivalents, what you simply are going to do is, number of milli equivalents of the substance is always equal to mass of the substance in grams divided by equivalent mass of the substance multiplied with 1000. This is one result. Second result, instead of number of moles, you will be writing number of millimoles. Number of millimoles multiplied by n factor of the substance, right? Which is also equal to normality of the solution multiplied by volume of solution in milliliters, right? These are the three results which I want you guys to remember in order to calculate number of milli equivalents of the substance, right? And remember one more thing, number of milli equivalents of the substance is always equal to number of gram equivalents of the substance multiplied with 1000. Do remember this result as well. These are the three important results which you need to take a note of, right? Okay. Now people, after noting down these three results, let's move on to something called as normality. Let's move on to something called as normality. Normality, which is denoted by capital N, right? How do we denote how do we define normality? It's simple. You all must be familiar with this, right? Normality of the solution is equal to number of gram equivalents of the solute divided by volume of solution in liters. This is one result by means of which you can calculate normality of the solution. Okay. Similarly, you can write it as mass of solute in grams multiplied with 1000 divided by equivalent mass of solute multiplied by volume of solution in milliliters. This is one more result by means of which you can calculate normality. The third and important result, normality of the solution is always equal to molarity of the solution multiplied by n factor of solute. multiplied by n factor of solute, right? This is one more result which you simply need to take a note of, right? I'm sure these are clear to everyone, okay? These were the results regarding the normality, okay? Perfect. One more thing. Most of the times when question comes either from redox, in redox, the question either comes from balancing part, which I'm sure that will be clear to you, right? Or the question will be directly from the oxidation states, or the question will be from equivalent concept, which is what you call as redox titration, right? What you simply are going to do in the equivalent concept, see guys, let's say you have got a balanced chemical equation as N1A plus N2B gives N3C plus N4B. This is a balanced chemical equation which I have, right? Now people, as per the equivalent concept is concerned, at the equivalent point you can say gram equivalence of A reacted should be equal gram equivalence of B reacted, which should be equal gram equivalence of C formed, which should be equal gram equivalence of D formed, right? Or you can write the same statement in terms of milli equivalence as well. You can say milli equivalence of A reacted should be equal milli equivalence of B reacted. This should be equal milli equivalence of C formed, which should be equal milli equivalence of D formed as well, right? And to calculate milli equivalence, to calculate gram equivalence, I've already given you the relations, right? Few minutes back, right? This is the simple statement which you guys are going to write in order to do these questions which are based on the equivalent concept, which are based on the redox titration, right? Okay, I'm sure this is again clear to everyone. Okay, let's exactly see if there are few more formulas in this redox. See, these are the calculation of n factors which we have discussed: number of moles, number of gram equivalents, number of gram equivalents, normality, relation between normality and molarity. This is done, right? Okay, volume strength of H2O2. There is a one simple result. In order to calculate the molarity of H2O2 aqueous solution, it is given as volume strength of H2O2 divided by 11.2. And most of the times, the volume strength of H2O2 will be given as per the equation. And if you'll be given with the volume strength of H2O2, just divide it with 11.2, get the molarity of H2O2 aqueous solution. Okay, this is one more result which I want you guys to remember. Yeah? Okay? Right? I'm sure it's clear to everyone. People, is everything clear till here so that I can move on to the atomic structure? Aryan, I have already give top 1000 MCQs of chemistry for NEET 2021. I think you can see the thumbnail. That session is tomorrow, right? Tomorrow we are going to do that session. Tomorrow we are going to do that session, yeah? Okay, let's move on to atomic structure formulas. Let's see what all formulas we have got in atomic structure. Okay. People, I'm starting this atomic structure formulas with something called as Planck's quantum theory. And as per Planck's quantum theory is concerned, energy associated with a photon is equal to h multiplied by nu, where nu is the frequency of the incident light, where nu is the frequency of the light. Okay, E is equal to h nu, or you can say E is equal to hc divided by lambda. This is the energy associated with one photon. This is the energy associated with one photon, right? Similarly, if I'll be having n number of photons, what is the energy associated with n number of photons? N times h nu, or you can say n times hc divided by lambda, right? This is the energy associated with n photons. Energy associated with n photons, correct? Remember one more thing, the value of h, as you all must be knowing, Planck's constant, which is 6.6 into 10 raised power minus 34 joules second, right? Or remember, the combined value of hc is either taken as 12400 electron volt angstroms if lambda is taken in angstroms, or you can take it as 1240 electron volt nanometer if lambda is taken in nanometers. Yeah, do remember this thing as well, right? In most of the questions, you take the direct value of Hc either as electron volt angstroms or electron volt nanometers, right? Okay. And remember at the same time, 1 electron volt is nothing that is 1.6 into 10 raised to the power minus 19 joules. Do remember this conversion as well. This might be helpful sometimes, right? Okay. Now people, talking about few more interesting things regarding Bohr's model. This is something which you need to remember, that's it, right? Talking some results from the Bohr's theory, from the Bohr's model. How do we do that? What are relations do we have in the Bohr's model? The first relation, that is to calculate the radius of the nth orbit. The radius of nth Bohr's orbit is equal to R0 n square divided by Z, where R0 is equal to 0.529 angstroms. This is the result by means of which you can calculate the radius of nth Bohr's orbit of any single electron species. From this result, you can compare the radius of two Bohr's orbits, R1 divided by R2 for example. R1 divided by R2 is equal to N1 square divided by N2 square multiplied by Z2 multiplied by Z1. This is the formula by means of which you can compare the radius of two Bohr's orbits of two different single electron species, right? I'm sure this is clear to everyone. Similarly, there is one formula by means of which you can calculate velocity of the electron in the nth Bohr's orbit, which is equal to V naught Z divided by N. What is the value of V naught? It is 2.18 into 10 raised power 6 meter per second, right? I hope you know this. Now, if you need to compare the velocity of the two electrons in two different Bohr's orbits, how do we do that? V1 divided by V2 is equal. It's going to be Z1 divided by Z2 multiplied by N2, and over here you're writing as N1. Yeah? This is one more result by means of which you can compare the velocities. The third result, to calculate the time period of the electron in the nth Bohr's orbit, right? It's equal to T naught multiplied by N cube 1 Z square, or you do not need this relation directly. You simply need to do one thing. You simply need to compare the time periods of the two electrons in two different Bohr's orbits, which is going to be, or you can write it like this: time period of the electron in the nth Bohr's orbit is directly proportional to N cube, inversely proportional to Z square. Do remember this as well. How do we calculate time period basically? Time period of the electron in the nth Bohr's orbit, it's equal to 2 pi r, right? Okay, 2 pi r divided by speed with which the electron moves, right? Radius of electron in the nth Bohr's orbit, you know. Velocity of the electron in the nth Bohr's orbit, you know the formulas. Put the formulas in this equation. You can write it like this: 2 pi multiplied by, instead of radius of electron in the nth Bohr's orbit, you can say R0 n square divided by Z, right? Vn, you can write as V naught multiplied by Z by N. Finally, you'll be getting this result. Over here. And in the similar way, whenever you need to compare the time periods of the two electrons in the two Bohr's orbits of two different hydrogen-like species, you'll be writing it as N1 cube divided by N2 cube multiplied by Z2 square multiplied by Z1 square, right? And similarly, you can talk about the frequency of the electron as well. Frequency is inverse of time period. You can say frequency of the electron in the nth Bohr's orbit, that is directly proportional to Z square and inversely proportional to N cube, right? From this result, you can compare the frequency of the two electrons moving in two different Bohr's orbits of two different hydrogen-like species, which is going to be V1 divided by V2 is equal to Z1 square divided by Z2 square, right? Multiplied by N2 cube divided by N1 cube. Do remember this one as well, right? Right, people? These are the results regarding the radius, regarding the velocity, regarding the time period. Now, talking about the results of the energy. How do we calculate the energy of the electron in any Bohr's orbit? Energy of the electron in the nth Bohr's orbit is equal, total energy I'm talking about, total energy of the electron is equal to minus 13.6 Z square divided by N square electron volts, right? This is one important result which you need to remember, right? This is the total energy. Okay, talking about only kinetic energy. Kinetic energy possessed by the electron in nth Bohr's orbit, that is 13.6 Z square divided by N square electron volts. Okay, and remember, potential energy of the electron in the nth Bohr's orbit, that's equal to 27.2 Z square divided by N square electron volts. Do remember this one as well. These are the three results regarding the energy. One is for total energy, one is for kinetic energy, and one is for potential energy. Yeah? Okay. Remember at the same time, the ionization potential, the ionization energy or ionization potential, how do we calculate that? Ionization potential is given by the formula 13.6 Z square divided by N square electron volts. Do remember this thing as well. Ionization potential. Okay. Now similarly, there is one formula called as Rydberg's formula, by means of which you can calculate the wavelength of the photon emitted when the electron makes a transition from higher energy state to lower energy state, right? And what is that result all about? We can say wave number, which is basically inverse of wavelength, is equal to R multiplied by Z square 1 upon N1 square minus 1 upon N2 square, right? And remember, 1 divided by R is nothing, that is 911.5 angstroms. Remember this thing as well, yeah? Right, people? Just a second, this is a minus sign over here. Yes, you're right, there's a minus sign over here. I forgot to write it, yeah? Now it's perfect? Now it's perfect? Okay, so this is how you calculate the wavelength emitted when the electron makes a transition from higher energy state N2 to lower energy state N1. Yeah, I'm sure it's again clear to you, right? And people, one more result which you must have come across in the Bohr theory, that's equal to MVR. MVR is equal to NH upon 2 pi. The angular momentum of the electron is the integral multiple of H upon 2 pi. One important result of the Bohr's theory, right? Similarly, you might have come across with one relation, that is mv square divided by r is equal to k times ze square divided by r square. This is one more result which you might have come across. Basically from these two results, from the last two results, you get all these results of velocity, energy, whatever, right? From the last two results. So do remember these two results as well. These are very important, okay? So this was about the angular momentum. This was about the centripetal force, okay? Now there are few more relations in the Bohr theory which you all must be knowing. How do we calculate that? The maximum number of spectral lines obtained, when the electron makes a transition from higher energy state to lower energy state. That's given as N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2, where N2 is the higher energy state, N1 is the lower energy state. The maximum number of spectral lines obtained is given by this result, right? Okay. And when the electron makes a transition from higher energy state N to lower energy state 1, how many maximum spectral lines do we get? We get it from the formula N multiplied by N minus 1 divided by 2, right? So this is the result which we get when the electron makes a transition from higher energy state N to shell number 1. These are the spectral lines which we obtain, okay? Yeah, I'm sure this is again clear to you, right? What all do we have? Okay, one more result. MVR is equal to N times lambda. I hope you know this part as well. I know you know this part as well, right? And at the same time, one more thing. As per de Broglie's hypothesis, lambda is equal to H upon P. As per de Broglie's hypothesis, lambda is equal to H upon P. Or you might have studied one more relation, that is kinetic energy is equal to P square divided by 2m. Right? So from here you can calculate the momentum. That's going to be 2m kinetic energy under root like this, right? So you can calculate the de Broglie's wavelength as H upon under root of 2m kinetic energy as well. This is one more result which you can calculate. Yeah? Right, people? This is something which you all must have heard, must have studied with me itself. Right? Lambda is equal to H upon under root of 2m Ke. Okay? Now, talking about something called as photoelectric effect and all. Okay? Let's move on. Let's see how many relations we have covered till now. Planck's quantum theory, A is equal to h nu, hc divided by lambda, right? Okay, if we talk about the photoelectric effect, these are the results which I want you guys to remember related to the photoelectric effect. This is the energy of incident light. This phi stands for work function of the metal. This is maximum kinetic energy with which electron moves after the removal from the metal surface, right? EI is the incident light energy which is equal to h nu. Phi naught is the work function h nu naught, kinetic energy maximum. H nu you can write in the form of Hc divided by lambda. H nu naught you can write in the form of Hc by lambda naught. This is kinetic energy maximum, right? Or you can calculate maximum kinetic energy from here, which is going to be equal to H nu minus H nu naught, right? Or you can write the same way as you can write kinetic energy maximum is equal to Hc divided by lambda minus Hc divided by lambda naught. And this is one important curve related to kinetic energy versus frequency, right? As you can see, kinetic energy versus frequency. Kinetic energy versus frequency, right? What is the curve all about? It's going to be a straight line. It's going to be a straight line with the positive slope and the negative intercept, right? Okay, it's simple, people. It's simple. Kinetic energy maximum is equal to H nu minus H nu naught. Now you need to plot a curve between maximum kinetic energy and frequency of the incident light, right? This is, for example, your Y. This is your X. This automatically becomes M, and this becomes the intercept with the minus sign over here. Y is equal to mx minus c. Y is equal to mx minus c is going to be a straight line, right? It's simple. Yeah? Or at the same time, you can do one more thing. Instead of maximum kinetic energy, you can directly write as E times V naught, right? Where V naught is the stopping potential. Instead of kinetic energy maximum, you can directly write as E times V naught, where V naught is the stopping potential and this nu naught is the threshold frequency. Yeah? I'm sure you all must have come across with this one as well, right, people? One more thing. This is something which I told you, kinetic energy versus the frequency of the incident light. Now, talking about the stopping potential versus frequency of the incident light. See guys, the relation which I told you, that's going to be H nu is equal to H nu naught plus kinetic energy maximum. Instead of that, you can write as EV naught, right? Now, I need to plot a curve between V naught and V. So, I'll be writing it as V naught is equal to H divided by E times nu plus H divided by E times nu naught, correct? V naught I'm plotting along y-axis, yeah? So this is my y, this is my y coordinate, okay? And nu I'm plotting along x-axis, so this is my x coordinate, correct? So this automatically becomes my slope and this automatically becomes my intercept. Y is equal to mx plus c. Just a second. Is it minus or plus? This is minus sign in between. Just a second, sorry. This is minus sign in between, right? This is minus sign in between. So y is equal to mx minus c. The curve is again going to be like this. And what is the slope of the curve? Slope means the value of m. The value of m over here is equal to h upon e. I'm sure you all would have come across with these curves as well. Yeah? Okay? Right, people? Okay, radius of nth orbit, this is something which we have discussed. Velocity, something we have discussed already, right? Energy, something we have discussed already, correct? De Broglie's hypothesis, these are the results which I want you guys to remember. Lambda is equal to h upon p, lambda is equal to under root of 2 mke, lambda is equal to under root of 2 qvm. When a charged particle q is accelerated under the potential difference of v, how do we calculate the de Broglie's wavelength associated with that particle? That's absolutely going to be equal to h upon under root of 2 qvm, where v is the potential difference under which the charged particle is being accelerated, right? Q is the charge possessed by that particle, m is the mass of that particle, right? And this result is directly valid for electron only. This result is directly valid for electron, yeah? Okay, lambda is equal to 12.27 divided by under root of v angstroms, right? And this v is the potential difference with which the electron has been accelerated, and this lambda is the de Broglie's wavelength associated with the electron which is accelerated under the potential difference of v. The last result is only valid for the electron, right? Okay. Talking about something called as Heisenberg's uncertainty principle, as you all must be knowing, it's impossible to determine the exact position and the momentum of the electrons simultaneously with 100% accuracy, right? Delta x dot delta p is greater or equal to h upon 4 pi. Delta x is something which we call as error in position. Delta v is something which we call as error in velocity, right? Delta p is something called as error in momentum, right? Greater or equal to h upon 4 pi. Or you can write the same way in this form as well. You can say delta x dot delta v is greater or equal to h upon 4 pi m. Most of the times you use this equation and get the equations done, right? Most of the times when the equation comes from the Heisenberg's uncertainty principle, this relation is used and question is to be solved, right? I'm sure this is again clear to you. Okay, delta x dot delta v is greater or equal to h upon 4 pi m. Okay, Now people, one question from which question frequently comes. One topic from which question frequently comes. How do we calculate angular nodes? How do we calculate radial nodes? Let me first of all tell you, total nodes is given by the formula n minus 1, right? Angular nodes is given by the formula L. Radial nodes is calculated as n minus L minus 1, right? These are the formulas by means of which you can calculate the total nodes, angular nodes, radial nodes, where L is the azimuthal quantum number, n is the principal quantum number, right? L is the azimuthal one, n is the principal quantum number. And remember, these radial nodes are also called as spherical nodes as well. These radial nodes are also called as spherical nodes as well. I'm sure this is again clear to you, right? Okay. So I think with this, all the formulas of atomic structure are done. Okay, one more thing, orbital angular momentum. How do we calculate orbital angular momentum? It is equal to under root of L into L plus 1 multiplied by h upon 2 pi. Yeah? Okay. How do we calculate spin magnetic moment? Spin magnetic moment is calculated as under root of, spin angular moment, under root of s into s plus 1 multiplied by h upon 2 pi, right? This is how you calculate the spin angular momentum as well, right? Under root of s into s plus 1 h upon 2 pi. Yeah? Right, people? And at the same time, do remember these three results as well. Total number of subshells in a given shell is always equal to the value of n, where n is the principal quantum number, right? Number of orbitals in a given shell is equal to n square. Maximum number of electrons in a particular shell is always equal to 2n square. I'm sure all this is clear to you. Now let's move on to something called as states of matter, right? I think everything about the atomic structure, whatever formulas are there, those are all done. If the question comes the formula based, the question will be related to these formulas only, yeah? Right, guys? Okay, moving on to something called as states of matter. In the states of matter, you have got first 4 gas laws, right? Just a second. You have got 4 gas laws. Right? One is called as Boyle's law. One is called as Charles' law. One is called as Gay-Lussac's law. And one is called as Avogadro's law. Right? In the Boyle's law, number of moles of the gas and temperature of the gas, both the things are kept constant. In the Charles' law, number of moles and pressure of the gas, both are kept constant. Right? In the Gay-Lussac's law, number of moles and volume of the gas are kept constant. And in the Avogadro's law, remember, pressure and temperature of the gas, both are kept constant. Yeah? Okay, as per Boyle's law, pressure is inversely proportional to volume of the gas, or you can say PV is equal to constant. This is something which we call as equation of state for the isothermal process as well, right? Or you can get one more relation from here, that is P1 V1 is equal to P2 V2, where P1 is the initial pressure of the gas, V1 is initial volume, P2 is final pressure, V2 is final volume of the gas, right? Similarly, as per Charles' law is concerned, volume is directly proportional to temperature in Kelvin, or you can say V is equal to K multiplied by temperature in Kelvin, right, people? Okay, and remember at the same time, V1 divided by V2 is equal to T1 divided by T2, correct? This is one important result which I want you guys to remember. At the same time, volume of the gas at a given temperature T degrees centigrade is equal to V0 plus V0 divided by 273 multiplied by temperature in degrees centigrade. This is the formula by means of which you can calculate the volume of the gas at any temperature T degrees centigrade, right? Okay. Now, if you talk about the Gay-Lussac's law, as per Gay-Lussac's law is concerned, pressure of the gas is directly proportional to temperature of the gas in Kelvin, or you can say P is equal to K multiplied by T, where K is the Gay-Lussac's constant, or you get the result from here, P1 divided by P2 is equal to T1 divided by T2. This is one more result from here, right? Or you can say pressure of the gas at any T degree centigrade is equal to P0 plus P naught divided by 273 multiplied by temperature in degrees centigrade, right? Remember, this V naught is the volume of the gas at 0 degrees centigrade. This P naught is the pressure of the gas at 0 degrees centigrade, right? Similarly, we have got Avogadro's law. In the Avogadro's law, you can clearly say volume is directly proportional to moles, or you can say V is equal to K multiplied by N, or you can say V1 divided by V2 is equal to N1 divided by N2. These are the results related to the gas laws. I'm sure you all must be knowing about this, right? Okay? Right, people? Now, one more important thing. What is the value of this Charles constant? What is the value of this Gay-Lussac's constant, right? What is the value of this Boyle's constant? Okay? See guys, have a look. If I'll be combining the gas laws, if I'll be combining the Boyle's law, Charles law and Avogadro's law, if I'll combine Boyle's law, Charles law and Avogadro's law, I'll be getting the ideal gas equation, as you all must be knowing. On combining the three gas laws, Boyle's law, Charles law and Avogadro's law, I'll be getting an equation, that's what we call as ideal gas equation. PV is equal to nRT. This is something which we call as ideal gas equation, right? What is this R over here? R is what we call as universal gas constant, and it has got three values. It has got three values. One is 8.314 joules per Kelvin per mole. This is one value of R. The second value of R is 0.0821 atm liter per Kelvin per mole. The last value of R is going to be 1.98, or instead of it, you can write 2 calories per Kelvin per mole, right? Okay, and in order to reduce the calculations, you can write, instead of 0.0821, you can write 1 divided by 12, right? And instead of 8.314, in order to reduce the calculation, you can write it as 25 divided by 3. 25 divided by 3, in order to reduce the calculation, I'm saying, right? Okay. Right, people? Now at the same time, one more thing. What was the equation related to the Boyle's law? That was PV is equal to constant. This was the equation of state for the isothermal process as per Boyle's law, right? This K is what we call as Boyle's constant. If I'll compare these two equations, I'll be getting the value of K, which is simply going to be equal to nRT, right? So K, which is what we call as Boyle's constant, that's equal to nRT, right? Okay. Similarly, if you talk about the Charles law, as per Charles law, V is equal to KT. V is equal to KT. If I compare V is equal to KT with V is equal to nRT by P, what do I get? I get K is equal to nR by P, right? And K is something which I call as Charles constant. It is equal to nR divided by P. Similarly, Gay-Lussac's constant K is going to be nR divided by V. Do remember this thing as well. Yeah? Right, people? Clear till here? Yeah? Okay, moving on. This was about the ideal gas equation part. There is something called as density form of ideal gas equation. See, as per your basic ideal gas equation, PV is equal to nRT, right? Right, people? At the same time, there is one more form, PM is equal to DRT. This is something which we call as density form of ideal gas equation. PM is equal to DRT. This is something which we call as density form of ideal gas equation, where D stands for density of gas, M stands for molar mass of the gas, P stands for pressure of the gas, R is the gas constant, T is the temperature of the gas, right? Okay, I'm sure it's again clear to you. Now after this, you have got something called as Dalton's law of partial pressure, if you remember, right? And as per Dalton's law of partial pressure, if I'll be having two or more than two chemically non-reacting gases present in the container, let's say these are three chemically non-reacting gases present in the container, the total pressure of the mixture, I'm representing by PS or PT, which is the total pressure of the mixture. The total pressure of the mixture as per Dalton's law is the sum of partial pressure of first, partial pressure of second, partial pressure of third, right? And how do we get the partial pressure of first? Partial pressure of first is calculated as total pressure of the mixture multiplied by mole fraction of first. Similarly, partial pressure of second is going to be equal to total pressure of the mixture multiplied by mole fraction of second. Similarly, partial pressure of third is going to be equal to total pressure of the mixture multiplied by mole fraction of third. I'm sure this is again clear to everyone, right? Simplest form of the Dalton's law of partial pressure. And if you talk about something called as effusion diffusion, right? As per Graham's law of effusion is concerned, rate of effusion is inversely proportional to square root of molar mass of the gas. This is something which you all must be familiar with, right? This is something which you all must be familiar with. rate of effusion or diffusion is inversely proportional to square root of molar mass of the gas. Or if I'll be having the gases present at same pressure and temperature, let's say I've got two gases present at same pressure and temperature, how do we compare their rates of effusions? Let me tell you, rate of effusion of gas 1 divided by rate of effusion of gas 2 will be equal to under root of molar mass of gas 2 divided by molar mass of gas 1, or instead of molar mass you can place density as well, density of gas 2 divided by density of gas 1, or you can write rate of effusion of gas 1 as volume of gas 1 coming out of the container in time t1 seconds, volume of gas 2 coming out of the container in time t2 seconds, right? Or you can write it as number of moles of gas 1 coming out of the container in time t1 seconds, number of moles of gas 2 coming out of the container in time t2 seconds. These are the results which I want you guys to remember, and these results are only valid when two gases are present at same pressure and temperature, right? But at the same time, let's say I've got two gases present in two different containers whose temperature is kept same but the pressure is kept different. Temperature is kept same, pressure is different. Let's say I've got two gases whose temperature is same but the pressure is different. How do we compare their rates of effusions? It's going to be R1 divided by R2 is equal to P1 divided by P2 under root of M2 divided by M1. P is the pressure of gas 1, V is the volume of gas 1 in the container, M2, M1, that are the respective molar masses, you all must be knowing that. Instead of R1, you can write V1 divided by T1. Instead of R2, you can write V2 divided by T2, right? Instead of V1, you can write N1 by T1. Instead of V2 by T2, you can write N2 divided by T2 as well, right? You can write N2 divided by T2. These are the results which you will be using when the temperature of two gases is kept same but the pressure is different, right? Okay, now let me tell you one more result. That is valid when both pressure and temperature of the gases are kept different. If I'll be having two gases, I'll be keeping their pressure and temperature different. How do we compare their rates of effusions? R1 divided by R2 is equal to under root of T1, just a second guys, it is equal to rate, just a second, rate is T divided by M, okay, T1 divided by T2 multiplied by M2 divided by M1, right? This is the result which you guys will be remembering in order to compare the rates of effusions of two gases which are present, whose pressure is different as well as temperature is different, right? And instead of R1, you can write V1 by T1. Instead of R2, you can write V2 divided by T2. And at the same time, instead of V1, you can write N1 by T1. And over here, you can write N2 divided by T2. These are the results which I want you guys to remember, okay? These are the results which I want every one of you guys to remember properly, right? Regarding the Graham's law of effusion and diffusion. Now, there is one more equation called as Kinetic Gas Equation. Kinetic Gas Equation is nothing that is PV is equal to 1 by 3 m V Rms square. Let me tell you, this relation is directly valid for 1 mole of ideal gas. This relation is valid for 1 mole of ideal gas, right? Talking about the different molecular speeds, if I talk about Rms speed, there are few formulas to calculate Rms speed. There are few formulas to calculate every speed. There are few formulas to calculate most probable speed as well. Let's get to know about those speeds. First of all, if I talk about Vrms, how do we calculate Rms speed? Rms speed is calculated by the first formula, under root of 3 RT divided by M. For 1 mole of gas, instead of RT, you can write PV. So it's going to be under root of 3 PV divided by M as well. Okay. If you keep this volume in the denominator, you get one more result. That's going to be under root of 3 times P divided by D, right? It becomes mass by volume, that becomes density. So these are the three results by means of which you can calculate RMS. And there is one result which is common, which is V1 square plus V2 square plus dash 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 divided by N ka root, right? This is one more way by means of which you can calculate RMS speed. So this result, and this result, these are the results by means of which we can calculate root mean square speed. Talking about the average speed, how do we calculate average speed basically? It's V1 plus V2 plus dash divided by what? Divided by number of molecules. V1 is the velocity with which the gas molecule first moves. V2 is the velocity with which gas molecule second moves, and so on, right? Okay. One more result about the average speed, which is going to be equal to under root of 8 RT divided by pi m or you can write under root of 8 PV divided by pi m, or you can say it's going to be equal to under root of 8p divided by pi multiplied by density of the gas, right? These are the results by means of which you can calculate every speed of the gas. And remember, all these molecular speeds, be it RMS, be it average, be it most probable, they are defined when the temperature of the gas is kept constant. When you keep the temperature of the gas fixed, at a fixed temperature of the gas, these speeds are basically defined, right? Do remember this thing as well, okay? Now talking about the most probable speed, so most probable speed of the gas is nothing, it is equal to under root of 2 RT divided by m, or instead of 2 RT divided by m, you can say 2 PV divided by m, right? Or you can write in the form of density as well, it's going to be equal to under root of 2p divided by d, right? Do remember these results for the different molecular speeds, yeah? And all these molecular speeds, they are defined only when the temperature of the gas is kept constant, right? Okay. And remember at the same time one more thing. I want you guys to remember one more thing. What is that going to be? At a particular temperature, if I'll be having a gas, right? Let's say I've got a gas. At a particular temperature, V RMS of the gas is more than V average, which is more than most probable, right? Do remember this result as well. At a particular temperature, Santosh is saying, sir, V average last formula is wrong. What did I write? V average last formula, where is the mistake? It might be some, can you just confirm it? Did I write the wrong formula for the V average? V average is nothing, that's equal to under root of 8 RT divided by pi m, right? Or you can write as under root of 8 PV divided by pi m. Yeah? Or you can write under root of 8p upon pi d. I think that's something which I wrote. Where is the mistake? You can just confirm it. You can check it out. Maybe I might be, some term might be missing. You can check it. You can let me know. Okay. All right. So when a gas is kept at a fixed temperature, at a particular temperature, V RMS for the gas is greater than V average, which is greater than V most probable, right? Okay. This is all about the molecular speeds. Now talking about the kinetic energy. Let me tell you, kinetic energy for 1 mole of a gas kept at a particular temperature is equal to 3 divided by 2 RT. This is how do we calculate kinetic energy for 1 mole of a gas which is kept at temperature T, right? Now if I say kinetic energy for n moles of gas, kinetic energy for n moles of gas kept at temperature T is equal to 3 divided by 2 nRT. Kinetic energy for 1 molecule of gas kept at temperature T is going to be equal to 3 divided by 2 kT, where K is what we call as Boltzmann's constant, whose value is equal to R divided by Na. R is gas constant, Na is Avogadro's number, so its value finally will be 1.38 into 10 raised power minus 23, right? This is the value of Boltzmann's constant. This is the kinetic energy for 1 mole of gas, kinetic energy for n moles of gas, kinetic energy for 1 molecule of gas, right? Okay, so do remember these results as well, correct? Now, after this, let's move on to something called as compressibility factor. Compressibility factor, which is denoted as Z, it has got certain formulas. One is PV divided by nRT. This is how you calculate compressibility factor. Second is V0 divided by VI. V0 is the observed volume or the volume of real gas. VI is the volume of ideal gas, right? Or you can call it as Pm divided by dRT. This is one more result of calculating the compressibility factor Z, right? Okay. So compressibility factor is simply a factor by means of which you can identify whether a gas is real or ideal. That's all. Yeah, that's all. So these are the formulas by means of which you can calculate the compressibility factor Z. Okay, and do remember one more thing. As the value of Z for the gas decreases, remember force of attraction between the molecules increases. Or you can say in the vice versa form, as the force of attraction between the gas molecule keeps on increasing, the value of Z for the gas keeps on decreasing. And remember, as the value of Z for the gas increases, do remember force of repulsion between the gas molecules, that increases, right? Do remember these 2 points as well. I'm sure it's clear to every single guy, okay? There is something called as compressibility factor, there is something called as Van der Waals gas equation. Van der Waals gas equation, that's nothing, P plus AN square divided by V square multiplied by V minus NB is equal to nRT, right? Okay, this is what we call as Van der Waals gas equation. Let me tell you, this AN square by V square, it gives me the idea about the force of attraction between the gas molecules, and this NB term, it gives me the idea about the size of the gas molecules, right? Okay, or you can say A and B, these are what we call as Van der Waals constants. A gives us the idea about force of attraction, B gives us the idea about the size, right? Remember, more the value of A for the gas, more is going to be the force of attraction between its molecules, and lesser is going to be its Z value, right? Similarly, more the value of B for the gas, more is going to be the size of the gas molecules. Do remember this thing as well, okay? So this is valid for n moles of real gas, okay? This is what we call as Van der Waals gas equation, okay? Perfect. Now, this AN square by V square, which gives us the idea about the force of attraction, it's something which we call as pressure correction factor. This NB, this is called as volume correction factor. Pressure correction factor, basically we represent it as delta P, and volume correction factor, we represent it as delta V. And let me tell you a few more important things. Remember delta P, which is the pressure correction factor, it's equal to AN square by V square, right? And at the same time, delta V, which is the volume correction factor, which is equal to NB. If I want you guys to get the units of A, the units of A can be calculated in this way, right? This is pressure, it's going to be ATM. Volume square, that means liter square, per mole square, right? These are the units of A. Similarly, the units of B, B is first of all going to be equal to delta V divided by N. Delta V is liter, N stands for mole, so liter per mole is the unit of B, okay? Liter per mole is going to be the unit of B, yeah? Right, people? Clear to everyone? Simple, more the force of attraction, more the value of A. Less the force of attraction between the molecules, less the value of A. This is something which we have discussed in detail. Yeah? Perfect, guys? More the value of A, okay. More the value of A, more the force of attraction, less the value of Z. More the value of B, more the size of the gas molecules. That's it. Some direct results. And there are some other results as well, as Karthik is saying, there are some other results as well for the liquefaction, that is critical temperature, critical volume and critical pressure. Do remove that as well, okay? And one important result, that is the compressibility factor value under critical conditions, that's always going to be equal to 3 by 8. Do remember this thing as well, okay? Compressibility factor under critical conditions. But before that, at low pressure, when the gas is kept at low pressure, at very, very low pressure, or simply let me keep it as low pressure, when the real gas is kept at low pressure and moderate temperature, what is the value of Z? Value of Z is going to be 1 minus A divided by VRT. So you can see the value of Z is clearly less than 1, which clearly says in the gas, attractive forces are dominating. Attractive forces are dominating, right? Similarly, at high pressure, when the gas is kept at high pressure, and moderate temperature, remember the value of Z is going to be 1 plus PB divided by RT, which clearly says Z value is greater than 1. That means repulsive forces are dominating. Repulsive forces are dominating. And remember, at very, very, very low pressure, remember the value of Z is equal to 1. That means your real gas, it behaves like the ideal gas. Do remember these things as well, okay? Right? Okay? Now people, at the same time, one more thing. Let's say I'm giving you a question like this. One simple question I'm giving you. Z versus P curve. Z versus P curve, right? Z versus P curve. You're different with these three curves like this. This is valid for the gas when its temperature was T1, temperature was T2, when its temperature was T3, right? You need to get the relation between T1, T2 and T3. Remember, that curve which lies closer to this Z is equal to 1 line will be having the more temperature. As simple as that. Do remember in this way. Okay, that curve which lies more closer to Z is equal to 1 line, its temperature will be high. So remember, T1 will be greater than T2, which will be greater than T3, right? Or there is one more way of doing the same, right? You need to see the compressibility factor versus temperature relation in the high pressure region and the low pressure region, right? You can talk in terms of that as well. Yeah, do remember this thing as well directly. I'm sure it's clear to everyone. So let's see exactly how we covered all the formulas. Gas laws, Boyle's law, right? All these formulas are discussed. In case of Charles' law, right? Gay-Lussac's law, ideal gas equation, density form of ideal gas equation. Okay, one more thing. This is something which we call as master equation. In the ideal gas, P11 divided by P2V2 is equal to N1T1 divided by N2T2. And if in equation, any term is kept constant, you are going to remove all those terms from this equation. For example, you are given the equation in which number of moles are kept constant. Or for example, pressure is kept constant. If pressure of the gas is kept constant, just remove P1, P2, use this equation in the equation. If for example, volume of the gas is kept constant in the equation, what you are going to do is, you are going to remove all these volume terms and finally you'll be using this equation in the equation, right? Similarly, people, if temperature of the gas is kept constant, just remove T1, T2 from here, use the final equation. So in short, whatever parameter is kept constant as per the equation, you are going to remove that parameter from this master equation, and the equation which you are left with, that's something which you will be using in the final equation, right? The way it's mentioned over here, correct? The way it's mentioned over here. All these things we have discussed in detail if you remember. Dalton's law of partial pressure, that's something which we have discussed, right? Graham's law of effusion diffusion, that's something which we have discussed. Kinetic gas equation, right? This is discussed too. Molecular speeds, its relations, it's discussed too, right? What are the things left? Compressibility factor. Z value less than 1 attractive force dominating, Z value greater than 1 repulsive force are dominating, right? Van der Waals gas equation, this is something which I told you, correct? Okay, let's move on to something called as thermodynamics now, okay? People, everything is clear till here? Everything clear till here? Yeah? Let's see what are the results from the chapter thermodynamics, yeah? Oh, Sai Kumar is saying, I forgot to give you the formulas for the quantum numbers. Its quantum numbers are simple. See, there is nothing. Principal quantum number, that's represented by N. Azimuthal quantum number by L. Magnetic quantum number by M. Spin quantum number by S. Remember, out of these 4 quantum numbers, this one, and this one, these 3 are the outcome. These 3 are the results of the Schrodinger's wave equation. The first three, these are basically the results of the Schrodinger's wave equation. On solving Schrodinger's wave equation, you get the value of N, you get the value of L, you get the value of M, right? Now talking about this L, people. This L value, it's from 0 to N minus 1, right? This M, it's going to be from minus L to plus L. And this S, it has got 2 values, that's plus 1 by 2 and minus 1 by 2. Plus 1 by 2 for clockwise spin, minus 1 by 2 for anti-clockwise spin, that's all, right? Right? Okay, now let's move on to something called as thermodynamics, right? Let's see what all results we need to remember from the chapter thermodynamics, right? Okay. See guys, first of all, giving you some basic idea. Whenever heat is absorbed by the system, Q value is taken to be positive, right? Similarly, whenever heat is released by the system, Q value is taken to be negative, right? First point. Second point. Whenever there is expansion of the gas means whenever the volume of the gas increases, that means expansion of the gas happens. During expansion, we always say work is done by the system. And W value is taken to be negative. In chemistry, I mean. In chemistry, W value is taken to be negative. Similarly, whenever there is compression, we always say work is done on the gas or on the system. And W value is taken to be positive, right? These are the sign conventions which you all must know before doing any sort of thermodynamics question, right? Sorry. Okay, now, how do we calculate work? The general expression to calculate work is going to be minus integral V1 to V2 P external multiplied by dV. This is the general expression to calculate work. Now, depending on whether the process is reversible or irreversible, we calculate work. In case of reversible processes, P gas, pressure of the gas, is almost equal to P external. And how do we calculate work? We say work done in any reversible process is equal to minus integral V1 to V2. Instead of P external, you can write P gas multiplied by dV. This is the result which you need to follow in order to calculate work done in reversible process. In case of irreversible processes, external pressure is kept constant. If external pressure is kept constant, right, you can calculate work done in irreversible process, right? You can take this P external out of this integral. So finally you get something like this. You get minus P external V2 minus V1, right? V2 minus V1. This is the result to calculate work done in irreversible isothermal process. Okay. Now people, talking about one more thing. What is that going to be? That's going to be the values of Cp, Cv and gamma for the ideal gas, right? Okay, before talking about that, remember Cp minus Cv is equal to R, right, for 1 mole of ideal gas. And you all must be familiar with the value of gamma, which is the Poisson's ratio, which is basically equal to Cp divided by Cv, right? Okay. For the monoatomic gas, remember, for the monoatomic gas, Cv value is equal to 3 by 2R, Cp value is equal to 5 divided by 2R, and gamma value is equal to 5 divided by 3. Okay. For the diatomic gas, or polyatomic linear, for diatomic or polyatomic linear gas, remember Cp is equal to 5 by 2R, Cv is equal to 5 by 2R, Cp is equal to 7 by 2R, and the value of gamma is going to be 7 divided by 5, right? And at the same time, for triatomic non-linear, or I can say polyatomic non-linear, for polyatomic non-linear, Cv value is equal to 3R, Cp value is equal to 4R, and from here you get the value of gamma as 4 by 3. And remember, as the atomicity of the gas increases, the value of gamma decreases. Do remember this as well. As the atomicity of the gas increases, as the atomicity of the gas increases, the value of gamma decreases. Do remember this thing as well, right? Now, moving on to something else. What is that? That's going to be Cv for the mixture. How do we calculate the molar heat capacity at constant volume for the mixture of gas, right? And how do we calculate Cp mixture as well? And how do we calculate gamma mixture as well? What is meant by all this? Let me tell you. For example, I'm given with a container. In this container, you have got some 3 chemically non-reacting gases, gas 1, gas 2 and gas 3. Let's say there are N1 moles of gas 1 in the container, N2 moles of gas 2 in the container, N3 moles of gas 3 in the container. Let's say molar heat capacity of gas 1 at constant volume is represented by Cv1. This is having Cv2, this is having Cv3. So Cv mixture is simply going to be equal to N1 Cv1 plus N2 Cv2 plus N3 Cv3 divided by N1 plus N2 plus N3, right? Cp mixture is simply going to be Cp minus Cv is equal to R, so it's going to be R plus Cv mixture, as simple as that. R plus Cv mixture. How do we calculate gamma for mixture? It's going to be Cp for the mixture divided by Cv for the mixture. As simple as that, right? And remember, for 1 mole of gas, Cp minus Cv is equal to R. For n moles of the gas, Cp minus Cv is equal to Nr, right? That's something which I assume you all must be knowing, right? Okay. One more thing. If I talk about the ideal gas, how do we calculate internal energy change delta U for the ideal gas? Delta U for the ideal gas is equal to QV. Remember, QV is the heat exchange between system and surroundings at constant volume, which is actually equal to delta U, and delta U is nothing. Delta U is integral NCV dt from temperature T1 to T2, right? Or if Cv was temperature independent, then you can write it as NCV delta T. If Cv was temperature independent, you can write it as NCV delta T, right? Similarly, for the ideal gas, delta H is nothing, that's equal to QP, heat exchange between system and surroundings at constant pressure, which is exactly equal to integral T1 to T2. It's going to be NCP dt, right? Or if Cp was temperature independent, you can write it as NCP delta T. Okay? Yeah? Right, people? Simple. Right? So delta U for the ideal gas, delta H for the ideal gas is calculated like this. Okay? Now, what is the relation between delta H and delta U? What is the relation between delta H and delta U? Okay, before talking about the relation between delta H and delta U, let me tell you, whenever the ideal gas undergoes isothermal process, delta U as well as delta H for the ideal gas is taken as 0, right? Do remember one more thing. Change in the value of a state function for any cyclic process is taken to be 0, right? Be it delta S, be it delta H, be it delta U, everything is equal to 0, right? As per your first law of thermodynamics, delta U is equal to Q plus W. This is something which you all must be knowing, right? And while using this relation, you need to be careful with the sign conventions, right? And units as well, okay? Remember, 1 atm liter, which is the unit of energy, is equal to 101.3 joules. And remember, 1 bar liter, it's equal to 100 joules. Do remember this as well, yeah? Okay, now talking about the relation between delta H and delta U. What is the relation between delta H and delta U? Yeah? See guys, have a look. First of all, the general relation between delta H and delta U, that's going to be delta H is equal to delta U plus delta of PV, right? This is the general relation between delta H and delta U for any system, okay? Now, if the system is the ideal gas, which is kept at constant pressure, at that time, delta H is written as delta U plus P delta V, because pressure of the gas is kept constant. I have kept P out. This is valid when the pressure of the system is kept constant, pressure of the gas is kept constant. Okay? Now at the same time, if volume of the gas is kept constant, I can say delta H is equal to delta U plus V delta P, right? When volume of the system is kept constant. If pressure as well as volume of the system will be changing, at that time delta H is equal delta U plus P2V2 minus P1V1. This is valid when pressure as well as volume for the gas changes. Okay? Now we will at the same time, one more thing. Have a look. For the gaseous phase reaction which is carried out at constant temperature, if I'll be having a gaseous phase reaction which is carried out at constant temperature, remember delta H is nothing, that's equal to delta U plus delta NGRT. This is valid for a gaseous phase reaction which is carried out at constant temperature. Do remember these relations as well, okay? Okay, one thing I forgot to tell you that about free expansion, right? If you talk about free expansion, that means expansion is in vacuum. P external is kept 0. If P external is 0, W is going to be 0. And remember, free expansion is always irreversible. It is always irreversible process. and W value in this case is kept 0, right? Well, free expansion is further of two types. One is called as iso, or one I'll be calling as adiabatic free expansion. If I do the adiabatic free expansion of ideal gas, okay, I'm taking the system as ideal gas. If I do the adiabatic free expansion of ideal gas, first of all, in case of free expansion, W value is 0. In case of adiabatic process, Q value is 0. If Q is 0, W is 0, that means delta U is 0. If delta U is 0, that means temperature of the system is constant. Or you can say delta T is 0, right? Okay. Or that process in which temperature of the system is kept constant, that's what we call as isothermal process as well. So remember, an adiabatic free expansion of ideal gas is isothermal as well, right? An adiabatic free expansion of an ideal gas is isothermal as well. Do remember this part as well. Similarly, you have got isothermal free expansion. You have got isothermal free expansion of an ideal gas. When we do the isothermal free expansion of an ideal gas, first of all, in free expansion, W value is 0. Since the process is isothermal, so temperature is constant. If temperature is constant, delta T is 0. If delta T is 0, that means delta U is 0. If delta U is 0, W is 0 as per first law, Q is equal to 0. And in which process Q is 0? For adiabatic process. So I can say an isothermal free expansion of ideal gas is adiabatic as well, right? An isothermal free expansion of ideal gas is adiabatic as well. I'm sure this is again clear to you. Okay. Now, we have got different types of thermodynamic processes: isothermal, isobaric, adiabatic, isochoric, and so on, right? Let me start directly with isothermal process. On one side, I'm writing reversible isothermal. Process. On another side, I'm writing irreversible isothermal process. Irreversible isothermal and reversible. How do we calculate work done in reversible isothermal and how do we calculate work done in irreversible isothermal process, right? Okay, check it out. See guys, work done in reversible isothermal process is calculated by the formula minus nRT ln of V2 divided by V1, or you can write it as minus nRT ln of P1 by P2, or you can convert the results in the logarithmic form as well. It's going to be minus 2.303 nRT log of V2 divided by V1, or you can write it as minus 2.303 nRT, it's going to be the log of P1 by P2. These are some results which you need to remember in order to calculate work done in reversible isothermal processes, okay? Yeah? Now, in case of irreversible isothermal process, how do you calculate work? I'll say work done in case of irreversible isothermal process, that's equal to minus P external V2 minus V1, right? Or you can write it as minus P external, instead of V2, you can write it as nRT divided by P2 minus nRT divided by P1. Okay? Or simply, you can take nRT common. If you take nRT common, it becomes 1 upon P2 minus 1 upon P1. Yeah? These are the results which I want you guys to remember in order to calculate work done in reversible isothermal and irreversible isothermal processes. And as you all must be knowing, in isothermal processes, temperature of the system does not change at all, right? Temperature of the system is kept constant. This is something which you all must be knowing. Delta T value for isothermal process is kept as 0, right? Okay, perfect. Yeah? I have no idea, Gayatri, for how long the session will go. Maybe for 1 more hour, right? Okay, now let's move on to something called as reversible adiabatic process and irreversible adiabatic process. Like, how do we calculate work done in reversible adiabatic and irreversible adiabatic? Right? In case of reversible adiabatic processes, first of all, in case of adiabatic process, as you all must be knowing, Q value is 0. If Q value is 0, delta U is equal to Q plus W, or you can say W reversible is equal to delta U, and delta U is nothing, that's equal to N CV delta T, which is T2 minus T1. CV, all of you must be knowing. CV, all of you must be knowing, that's equal to R divided by gamma minus 1. right? It's going to be T2 minus T1, correct? Or you can say work done in reversible adiabatic process is equal to nRT2. Instead of nRT2, I can write P2V2. Instead of nRT1, I can write P1V1 divided by gamma minus 1. You can use any of these results among all to calculate work done in reversible adiabatic process, right? Okay. Similarly, in case of irreversible adiabatic process, how do we calculate work? Work done in irreversible adiabatic process is calculated as minus P external, V2 minus V1, this one of the result. Similarly, you can convert it into different result as well. Instead of V2, you can write nRT2 divided by P2, right? Instead of V1, you can write nRT1 divided by P1. Or you can take nR as common, it becomes T2 by P2 minus T1 divided by P1. These are the formulas by means of which you can calculate work done in reversible adiabatic and irreversible adiabatic processes, right? Now comes one more point. That is the calculation of final temperature in reversible adiabatic and irreversible adiabatic. How do we calculate the final temperature in case of reversible and irreversible adiabatic processes? Let's check it out too. In case of irreversible adiabatic processes, we know delta U is equal to W because Q value is 0. Instead of delta U, you can write NCV T2 minus T1 is equal, instead of W, it's basically W irreversible, which is going to be minus P external V2 minus V1. This is one of the result which you can use in order to calculate final temperature of the gas T2, right? At the same time, I can convert it into different form as well. I can write this N. Instead of CV, I can write this R divided by gamma minus 1. It's going to be T2 minus T1 is equal minus P external. Instead of V2, you can write this NR T2 divided by P2 minus NR T1 divided by P1. NR, 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 everywhere it gets cancelled out. So the final result becomes T2 minus T1 divided by gamma minus 1 is equal minus P external T2 divided by P2 minus T1 divided by P1. Correct? Okay. This is one of the result to calculate final temperature. This is one more result to calculate final temperature in case of irreversible adiabatic process, right? Okay. Now similarly, in case of reversible adiabatic processes, how do we calculate final temperature? First of all, this PV raised power gamma is equal to constant. This is what we call as equation of state for the reversible adiabatic process, right? There are few results by means of which you can calculate final temperature of the system. That's going to be equal, that's one of the result is going to be T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. This is one of the result by means of which you can calculate final temperature of the system, right? Okay. Now people, at the same time, I can write P1 raised power 1 minus gamma multiplied by T1 raised power gamma is equal to P2 raised power 1 minus gamma multiplied by T2 raised power gamma. This is one more result by means of which you can calculate final temperature of the system T2, right? Do remember these results. These are valid for to calculate the final temperature of the system in case of reversible and irreversible adiabatic processes, right? Okay, one more thing. If you talk about any isochoric process, in case of isochoric processes, we know volume of the system is kept constant. If volume of the system is constant, you can say delta V is equal to 0. If delta V is equal to 0, W value clearly you are going to take as 0, right? This is something which you all must be familiar with, yeah? Okay, I'm sure it's clear to everyone. Okay, moving on, let's see what our formulas we have discussed. This is something which you all must be knowing, isothermal, isochoric, isobaric, right? IUPAC sign convention, this is something which we have done. First law, delta U Q plus W. Calculation of heat, okay. If you talk about the heat capacity is nothing, dQ divided by dt, its units are joules per degree centigrade, right? Similarly, if you have molar heat capacity, which I denote by Cm, okay, it's basically equal dQ divided by ndt, and its units are joules per mole per Kelvin, right? And this formula we have already used, Cv is equal to R divided by gamma minus 1, yeah? Okay. Similarly, people's specific heat capacity, right? It's calculated as dQ divided by mdt, right? These are the units of it. And work done, this is something which I've told you. In case of isobaric process, W is simply equal to minus P external V2 minus 1. In case of isochoric process, W is equal to 0. Now, in case of adiabatic process, reversibly, this is how we calculate work. Irreversibly, this is how we calculate work. These are different results. Calculation of final temperature we have discussed, yeah? Okay, enthalpy and internal energy relation, this is something which is discussed too. Okay. Okay, entropy. This is the general formula by means of which you can calculate entropy change. Delta S system, if you want to calculate entropy change of the system, it's given as integral of dq reversible upon T. Small amount of heat exchanged between system and surroundings reversibly divided by temperature, right? That's how you calculate it, okay? And people, entropy calculation for an ideal gas undergoing expansion or compression. How do we calculate? See, whenever I'll be having the ideal gas, when it undergoes expansion or compression, how do we calculate its entropy change? There is a formula, there are two formulas for that. These are the two formulas which you want to remember in order to calculate entropy change for the ideal gas which undergoes expansion or compression, right? Okay, these are the two results by means of which you can calculate delta S gas, yeah? And remember at the same time one more thing. If during any process delta S total comes out to be 0, or wait just a second. Okay, remember if delta S total, that means entropy change of the universe for the system comes out to be positive. Sorry, not for the system. If entropy change of the universe, which I'm representing by delta S total, if it comes out to be greater than 0, we say the process is irreversible. The process is irreversible and spontaneous at the same time. For any process by means of which delta S total comes out to be less than 0, we say the process is non-spontaneous, right? And if delta S total for any process comes out to be 0, we say the process is supposed to be at equilibrium, right? Or you can say it is a reversible process. This is the criteria by means of which you can talk about the spontaneity of any process in terms of entropy, right? If delta S total, it's not entropy change of system or entropy change of surrounding. It is delta S total, entropy change of the universe. This is entropy change of the universe. This is entropy change of the universe, right? Okay, do remember these things as well. Yeah? Okay, talking about something called as Gibbs function, or you call it as Gibbs free energy. It is one of the parameter, basically by means of which we can talk about the spontaneity of any process. Delta G, which you all must be knowing, at constant pressure and temperature, delta G for the system is equal to delta G, delta H minus T delta S, right? Delta G is equal to delta H minus T delta S. If for any process delta G comes out to be negative, we see the process spontaneous. If delta G comes out to be positive for any system at constant pressure and temperature, we see the process non-spontaneous. And if delta G for the system at constant pressure and temperature comes out to be 0, we see the process reversible, right? Okay, right? And this equation is something which you call as Gibbs-Helmholtz equation as well. If delta G for the system at constant pressure and temperature less than 0, process spontaneous, greater than 0, non-spontaneous, equal to 0, the system is supposed to be at equilibrium. Now with this, let's move on to something called as equilibrium only, yeah? Right, people? This week's schedule is just going to be for you people. See, tomorrow it's going to be that 10-hour wala session in which I'll be discussing some 1,000, 1,100 equations, right? Okay, and after that we'll be doing some mega mock tests as well, right? Everything will be done, relax. Okay, equilibrium. First of all, how do we write the equilibrium constant? Equilibrium constant of the reaction is written as rate constant of the forward reaction divided by rate constant of backward reaction. Rate constant of forward reaction to the rate constant of backward reaction is something which we call as equilibrium constant in general, right? Okay. Right, people? Now, how do we write its expression? Its expression, as you all must be knowing, product of active masses of products raised to the power of their stoichiometric coefficients divided by product of active masses of reactants raised to the power of their stoichiometric coefficients, right? And whenever I'll be having any reactant or product in aqueous form, its active mass is taken as its concentration. If it is in gaseous form, its active mass can be taken as its pressure or its concentration. If I'll be having any reactant or product in solid form or pure liquid form, its active mass is generally taken as unity, right? That's something which you all must be knowing, correct? This is the value of Kc, concentration, product of concentration of products raised to power their stoichiometric coefficients divided by product of concentration of reactants raised to power their stoichiometric coefficients. Similarly, if you want to write the Kp expression, it is simply going to be equal to product of partial pressure of products raised to power their stoichiometric coefficients divided by product of partial pressure of reactants raised to power their stoichiometric coefficients, right? Relation between Kp, Kc, this everyone knows, I believe. Kp is equal to Kc RT raised to power delta N, right? And how do we calculate delta N? Number of moles of gaseous products minus number of moles of gaseous reactants, right? Okay. Similarly, reaction quotient, just give me a second, guys. Okay. If we talk about the reaction quotient expression is written in the same way as we write the expression for equilibrium constant, right? It's going to be equal to concentration of, product of concentration of products raised to power their powers, raised to power their stoichiometric coefficients, divided by product of the concentration of reactants raised to power their stoichiometric coefficients. But all these concentrations are taken at any time apart from equilibrium, right? Okay. Degree of dissociation, alpha, number of moles of reactants dissociated divided by initial moles of reactants taken. This is something which you all must be familiar with. Ostwald's dilution law, alpha, right? As per Ostwald's dilution law, if you remember, with dilution, alpha value for a weak electrolyte that increases, right? With dilution, degree of dissociation of a weak electrolyte increases. Similarly, how do we write dissociation constant of a weak acid? This is how you write the dissociation constant of weak acid. Ka is equal to C alpha squared divided by 1 minus alpha, right? This all you must be knowing. Similarly, for weak base, you can write Kb is again equal to C alpha squared divided by 1 minus alpha. Then depending on whether you can neglect alpha or not, right? That's a different debate. Yeah? Okay. For a weak base, Kb is equal to nothing. For a weak base, you can say Kb is equal to C alpha squared divided by 1 minus alpha. From there, you can calculate alpha as well. Yeah? Okay, ionic product of water. Kw is equal to concentration of H positive multiplied by OH negative. This is valid at all temperatures, but particularly at 25 degrees centigrade, Kw is equal to H positive concentration multiplied by OH negative concentration, which is going to be equal to 10 raised power minus 14. This is valid only at 25 degrees centigrade, right? And finally, you get one more result which is important. P of Kw is equal to pH plus pOH, which is equal to 14 exactly. Yeah? Okay. Do remember this? This is only valid at 25 degrees centigrade, right? Okay. If you talk about the acidity and pH, how do we calculate pH? pH is nothing, that is minus log of H positive concentration. Simply P stands for minus log, that's it. P stands for minus log. If I say pOH, it means minus log of OH negative concentration. If I say P of Kb, it means minus log of Kb, right? Okay. And remember, if pH of the solution is given, you can calculate directly the H positive concentration, 10 raised power minus pH. If pOH of a solution is given, you can directly calculate OH negative concentration, 10 raised power minus pOH. If P of Ka is given, you can calculate Ka value, 10 raised power K minus K, right? All these things you all must be knowing. Salt hydrolysis. First of all, salt hydrolysis of, if I'll be having a salt of a strong acid and a strong base, its hydrolysis is not possible. That's something which you all must be knowing. When I do the hydrolysis of the salt of the strong acid and weak base, how do we calculate its various parameters? First of all, remember, when we do the hydrolysis of the salt of a strong acid and weak base, this is how you calculate pH, 7 minus half of P of Kb plus log of C, where C is the concentration of salt. And at the same time, degree of hydrolysis H is equal to under root of hydrolysis constant Kh divided by C, and Kh particularly, hydrolysis constant is equal to Kw divided by Kb, and C is the concentration of salt, right? This is when we do the hydrolysis of salt of strong acid and weak base. Similarly, when we do the hydrolysis of strong base and weak acid, these are the results to calculate pH and H over here. Similarly, when we do the hydrolysis of weak acid and weak base, we have got again 3 more results by means of which you can calculate pH, you can calculate hydrolysis constant, right? Everything can be done. Degree of hydrolysis H, okay? Yes, all these formulas are important. If the question comes from salt hydrolysis, you'll be given with all the values. You're just supposed to remember these. And put the values into these equations and kill the equation. That's all. Okay. Similarly, if we talk about mixed buffers, mixed buffers are of 2 types, right? Acidic, basic. For acidic buffers, you'll be asked to calculate pH. For basic buffers, you'll be asked to calculate pH. And pH for the acidic buffer is equal to P of Ka plus log of concentration of salt divided by concentration of acid. Similarly, P of OH for the basic buffer is equal to P of Kb plus log of conjugate divided by concentration of the base, right? These are the two results which you need to remember as well, right? This is called as Henderson's equation. pH is equal to P of K plus log of concentration of conjugate divided by concentration of acid, yeah? Solubility product, you all must be knowing. This is the direct result which you can remember in order to calculate KSP value, solubility product, yeah? Okay, or let me show it to you. How come we get this? See guys, if I'll be having a sparingly soluble salt as AXBY, first of all, it will undergo dissociation as X times AY positive plus Y times BX negative. Let's say solubility is X, so concentration of AY positive is X times S, concentration of BX negative is Y times S. If we write the expression for KSP, it's going to be equal to concentration of A plus Y raised to the power X multiplied by concentration of B minus X raised to the power Y, right? This value is given to me as X times S raised to the power X multiplied by Y times S raised to the power Y. Just to do a little bit of calculation, you'll be finally getting this as the answer. This is the general way of writing KSP, okay? Right? Right, people? So this was about the equilibrium, and these were some of the formulas which were related with the chapter equilibrium, right? Now solid state, it does not have many formulas, right? So we have to study basically three different unit cells, right? One is simple cubic unit cell, body centered, face centered, as you all must be knowing. In case of simple cubic unit cell, what all parameters you're going to remember? In case of BCC and FCC, all these parameters you're going to remember over here. See guys, if I talk about simple cubic unit cell, what is the relation between R and A? R is equal to A by 2. What is the value of effective number of particles? That's 1. Coordination number 6, packing efficiency 52%, right? Body centered, a relation between A and R is equal to root 3A by 4, simple, right? If I talk about effective number of particles, Z, that's equal to 2 for BCC. Coordination number of each particle in case of BC, that's 8. And percent efficiency, that's equal to 68%. And if you talk about the percentage of voids you can also calculate 100 minus 68, which comes out to be 32, right? Yeah. Similarly, for FCC, you'll be remembering these parameters. R is equal to A divided by 2 root 2. Effective number of particles for FCC is 4. Coordination number of each particle in FCC is 12. Right? Percent efficiency is 74. Number of octahedral voids in case of FCC 4, number of tetrahedral voids is going to be 8, right? That's something which is a general result basically. Total number of octahedral voids is always equal to the value of Z, and total number of tetrahedral voids is equal to the value of 2 times Z for any unit cell, right? Okay. Similarly for hexagonal unit cell. For hexagonal unit cell, if you remember, for hexagonal unit cell, Z value is 6, right? Total tetrahedral voids are 12, octahedral voids are 6. Okay, coordination number of each particle in case of HCP, hexagonal unit cell, that's also equal to 12, and packing efficiency is again equal to 74 in case of hexagonal unit cell as well. Do remember that. Okay, density of the unit cell, it has got the general formula. Density is equal to Z multiplied by M divided by Na multiplied by A cube. This is something which you all must be knowing. Rahul, CCP means FCC. CCP means FCC. For FCC, Z is 4, right? Okay. Okay, examples of ionic crystals, right? If you remember your rock salt structure, NaCl structure, coordination number 6 is to 6, right? Cesium chloride, and remember people, there is a table given in your NCERT, and if from that table, you're going to remember their occupancy as well. You need to know exactly, in case of NaCl structure, where are the Na positives present, where are Cl negatives present. For example, if I talk about NaCl, Cl negative ions, they are present at the corners and at the face centers, and Na positives, they occupy all the octahedral voids, right? Similarly, you need to remember all the occupancy of the ions in these structures, right? Okay? Right, people? Yeah? That's something which you must be doing. In the solutions, everything you all must be knowing. One is Henry's law. Partial pressure of gas over the liquid is equal to Henry's constant multiplied by mole fraction of gas in the liquid. Yeah? Similarly, if you talk about Raoult's law, nothing. That's how you calculate partial pressures. P is equal to P naught A chi A, PB is equal to P naught B chi B. If you'll be having a solution containing two volatile liquids, the total pressure of the solution is nothing. That's going to be equal to PA plus PB, and PA is P naught A chi A, PB is P naught B chi B. As simple as that, right? Okay. Relative lowering in vapor pressure, this is the result, P naught A minus Ps divided by weight. This is what we call as relative lowering in vapor pressure, this result, okay? P naught A minus Ps divided by P naught A is equal to chi B, which can be written as NB divided by Na plus NB. And this result you can use in majority of the equations, right? P naught A minus Ps divided by Ps is equal to NB divided by Na, right? You can solve this question. Ritika, basically formulas are there only in physical chemistry. There are no formulas in inorganic chemistry, right? Yeah? Okay, elevation and boiling point, delta TB is equal to KB multiplied by molarity of the solution. That's something you all must be knowing. And molality formula, that's something which you know already. Similarly, you have got depression and freezing point, delta TF is equal to KF multiplied by M. KF is called as cryoscopic constant, yeah? Right? And people, osmotic pressure, pi is equal to CRT. That's something which you all must be knowing, where C is the concentration number of moles divided by volume of solution, as simple as that. Yeah, Van 't Hoff factor, you all must be knowing. In case of dissociation, I value is always greater than 1. In case of association, I value is always less than 1. In case of no dissociation, no association, I value is taken to be 1. And in case of dissociation, generally I is written as 1 plus n minus 1 into alpha. In case of association, I is equal to 1 plus 1 by n minus 1 into alpha, right? This is something which you all must be knowing. Similarly, we have got such few formulas in electrochemistry, like standard EMF. E naught of cathode minus E naught of anode. Standard reduction potential of cathode minus standard reduction potential of anode, right? Yes. Similarly, Nernst equation at 298 Kelvin. How do we write it? E cell is equal to E naught cell minus 0.0591 divided by N log of QC. This is something which you all must be knowing. Correct? This is how you write Nernst equation. And at the same time, if you write the same Nernst equation at equilibrium E cell value is 0. At equilibrium, E cell value is 0, so E naught cell result is going to be this one, 0.0591 divided by N log of KEQ. Yeah? Similarly, we will give free energy, delta G is equal to minus NF E naught cell, minus NF E cell, right? Or you can calculate delta G naught as well, which is going to be minus NF E naught cell, correct? Based on the value of E cell, you can talk about the spontaneity of the cell. You can say whether the cell will be working or not. For any cell whose delta G is negative, E cell is positive, the cell will be working like the normal galvanic cell. For any cell whose delta G is positive and E cell is negative, we say the cell does not work, right? This is one more result to calculate delta G naught minus 2.303 RT log of Kc, correct? These are very simple results which we have discussed many a times. This is how we calculate reduction potential of any given electrode, which is equal to standard reduction potential of the electrode, minus 2.303 divided by NF log of QC, you can say reaction quotient. Yeah. Similarly, oxidation potential you can calculate in the same way. Oxidation potential of the cell, of the half cell is equal to standard oxidation potential minus 2.303 RT divided by NF log of QC. That's how you do it. Concentration cells are the ones in which we use two same types of electrodes, right? I mean same electrodes. For example, two zinc electrodes, two copper electrodes we are going to connect. These concentration cells are basically of two types. One is called as electrolytic concentration cell. First of all, for any concentration cell, E naught cell value is taken to be 0. This is something which you all must be knowing. For any concentration cell, E naught cell value is taken to be 0. I hope you know this, correct? For the electrolytic concentration cell, it is just the concentration of the electrolytic solutions is kept different, rest everything is kept same, right? And this is how you calculate E cell, 0.0591 divided by N, where N for this reaction is 2, log of C2 divided by C1. C2 is the concentration of the cathodic container, C1 is the concentration of anodic container, as simple as that. Yeah? Okay. Now similarly, if I talk about electrode concentration cell, for the electrode concentration cell, what do we have? For the electrode concentration cell, concentration of two electrolytes is kept same, but partial pressure of the gases which are adsorbed on the plates, they are kept different, right? And this is how you calculate E cell for the electrode concentration cell, which is going to be 0.0591 divided by N log of P1 by P2. P1 is the partial pressure of H2 gas at the anode, and P2 is the partial pressure of H2 gas at the cathode, right? Therefore, you can talk about its spontaneity as well. You can make the criteria for the cells to be spontaneous, for the cells to be working like the normal galvanic cell. You can do that as well. Faraday's first law. By means of Faraday's first law, you can calculate the mass of the metal deposited, mass of the gas liberated, number of moles of metal deposited, number of moles of gas liberated, anything you can calculate. There is a simple formula. W is equal to EIT divided by 96500. Let me write that for you. W is equal to EIT divided by 96500. Okay. For example, W is the mass of substance deposited. At that time, E stands for equivalent mass of substance, I stands for current, T stands for time, 96500 is constant, right? Similarly, you can calculate the mass of gas liberated as well, which is going to be equal to equivalent mass of gas, I, T divided by 96500. As per Faraday's second law is concerned, number of gram equivalents deposited or liberated on every electrode will be the same, be it simple electrolysis or complicated electrolysis, right? Okay. Yes? Perfect. Similarly, there are many more results. Resistance, R is equal to rho L by A, right? Rho is called as resistivity. Similarly, we have got resistivity, RA divided by L. Similarly, we have got conductance, G is equal to A divided by rho multiplied by L. Yeah. Similarly, one more, conductivity, kappa is equal to 1 by R L by A, where L is the distance between the electrodes, A is the area of cross section of the electrode which is dipped in the solution. Okay. Similarly, molar conductivity, lambda m is equal to kappa multiplied with 1000 by molarity, right? Similarly, there will be equivalent conductivity as well, kappa multiplied with 1000 divided by normality, right? Okay. Equivalent conductivity, molar conductivity formulas. Relation between molar conductivity and equivalent conductivity. Molar conductivity is equal to equivalent conductivity multiplied by n factor of the solute which is in the solution. Yeah? Right, people? Similarly, Kohlrausch law, you all must be knowing. Molar conductivity at infinite dilution. This Kohlrausch law, molar conductivity at infinite dilution is the sum of molar conductivities at infinite dilution for its respective ions. Right? That's how we write the Kohlrausch law. It's simple. So moving on to chemical kinetics, rate of reaction, change in the concentration of either reactants or products in a given time interval. For a reaction, if I'll be having this as the reaction, how do we write the rate of disappearance, rate of appearance for reactants and products respectively? How do we write it? How do we write it? It's simple. Rate of disappearance of A is going to be equal to change in the concentration of A divided by time interval with the minus sign. Rate of disappearance of B, minus sign. Change in the concentration of B divided by time interval. Rate of appearance of C, plus sign. Change in the concentration of C divided by delta T. Similarly, rate of appearance of D is going to be plus times change in the concentration of D divided by delta T. If you talk about rate of reaction, just a second guys. If you talk about, for example, you have got a reaction like this, N1A plus N2B, it gives N3C plus N4D. For example, this is the reaction which we have. If I want to write the rate of reaction, I can write it with respect to A, with respect to B, with respect to C, as well as with respect to D. With respect to A, I'll start with minus 1 divided by N1, change in the concentration of A divided by dt, which is going to be equal to plus 1 divided by N2, sorry, not plus, minus because B is the reactant, minus 1 divided by N2, change in the concentration of B, divided by dt, which can be written in terms of C as well, plus 1 divided by N3, change in the concentration of C divided by dt, which can be written as plus 1 divided by N4, change in the concentration of B divided by dt. This is how you can calculate rate of reaction either with respect to A, with respect to B, with respect to C, or with respect to D. Choice is all yours, right? Okay. Now order of reaction. For the order of reaction, you need to write the rate law. And after writing the rate law, this M is what I'll be calling as the order of reaction with respect to reactant P. N is called as order of reaction with respect to Q. And M plus N, it gives me the overall order of the reaction, right? This is how you calculate units of rate constant for any nth order reaction, where N is the order of the reaction. 1 by units of time, 1 divided by units of concentration raised per N minus 1. N is the order of reaction, as simple. Yeah? As simple. For the zero order, first order, do remember their integrated rate equations. Integrate, let me write it by myself. Okay, for the zero order reaction, you know, AT is nothing that's equal to A naught minus KT, where AT is the concentration of reactant left at any time T, A naught is the initial concentration of reactant, T is the time taken, K is the rate constant. And similarly, T half for the zero order reaction is nothing, it's A naught divided by 2K, right? Okay, T 100% for the zero order reaction, remember that's going to be equal to A naught divided by K, yeah? Units of rate constant, you know, for the zero order reaction, okay? Similarly, what all do we have over here? Just a second. Okay, one more thing we can conclude from here. What is that going to be? Have a look. Just a second, people. If I need to calculate alpha for a zero order reaction, if I need to calculate degree of dissociation for a zero order reaction, how do we do it? Let's say I've got the reaction as A gives B. Let's say its initial concentration is A naught, this is 0. Finally, at time t, the concentration of reactant left is 80. Let's say these are the initial moles of reactant. Let's say these are the final moles of reactant left. Okay. Alpha, how do we calculate it? Number of moles of reactant dissociated divided by initial moles of reactant taken. Okay. How many moles of reactant have got dissociated? Initially, I had A naught moles. Finally, I'm left with 80 moles divided by initial moles, that's A naught. And people, 80 is nothing. 80 is equal to A naught minus KT. Right? Divided by what? Divided by A naught. A naught gets cancelled out. So finally you get alpha value for the zero order reactions as minus KT minus plus. This becomes minus plus KT divided by what? Divided by A naught. So remember, degree of dissociation of the zero order reaction depends on the initial concentration of reactant. This is the conclusion which I wanted you guys to remember. Yeah? Alpha for the zero order reaction is inversely proportional to initial concentration of reactant. Similarly, if you talk about first order kinetics, for the first order reactions, you have got different ways to write the integrate rate equation. One is going to be equal to ln of AT is equal to ln of A naught minus KT. This is one of the result. Second result is going to be equal to log of AT is equal to log of A naught minus K upon 2.303 multiplied by T. This is one more result, right, which you can use for the first order kinetics. In the similar way, you can write K is equal to 1 divided by T. It's going to be ln of A naught divided by AT, right? Or you can say K is equal to 2.303 divided by T. It's going to be log of A naught divided by AT. One more result, correct? There can be some other results as well. You can write AT is equal to A naught e raised power minus KT for the first order rate equation. Yeah? And at the same time, people, you can get the alpha value for the first order kinetics as well, for the first order reactions. What is going to be alpha value? Just a second. Alpha value is going to be equal to, say, number of moles dissociated divided by initial moles taken, right? Number of moles dissociated is again going to be equal to A naught minus AT, where A naught I'm writing as such, AT I'm going to write A naught e raised power minus KT divided by A naught, right? A naught everywhere gets cancelled out. So alpha value for the first order reactions comes out to be 1 minus e raised power minus KT. This is the value of alpha for the first order reactions, right? This is the value of alpha for the first order reactions. Similarly, there can be other results too for the first order reactions. For the first order reactions, there can be other results too. Let's try to find out those. Say, time taken to complete 50% of the reaction, or you can call it as the half-life of the reaction. It's written as ln of 2 divided by K, or you can write as 0.693 divided by K, right? These are all the results of first order, okay? These are all the results of the first order. Let me erase the zero order over here. Okay. Now similarly, remember, time taken to complete 75% of the first order reaction is equal to 2 times the half-life of it, right? Remember, time taken to complete 87.5% of the first order reaction is equal to 3 times half-life of it, right? Time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life of it. Do remember these results, and all these results are only valid for the first order reactions. All these results are only valid for the first order reactions, right? Right? Time taken to complete 75%, 2 times half-life, 87.5%, 3 times half-life, 99.9%, 10 times half-life, right? Do remember this thing as well. Yeah? And people, there is one more thing which you need to remember. What is that? For the first order reactions, do remember a few more things. What is that? AT is equal to A naught 1 divided by 2 raised power n, where n is something which we call as number of half-lives, which is denoted as T divided by T half. Number of half-lives, yeah? number of half-lives. N, correct? Number of half-lives. These are all the results which are valid for your first order reactions. I'm sure it's clear to everyone. Yeah? Okay. Time taken for the 75, this is something which I've told you. Right? Okay, the last thing, which is the Arrhenius equation. Arrhenius equation is nothing. Rate constant K is equal to A, E raised power what? E raised power minus EA divided by RT. Correct? As per Arrhenius equation is concerned, on increasing the temperature of the reaction, rate constant of the reaction increases and eventually rate of the reaction increases. And for every 10-degree rise in the temperature, rate of reaction almost doubles. Rate of reaction almost doubles. Do remember this thing as well, right? Now people, you can convert this into the logarithmic form as well. If I multiply throughout by ln, it becomes ln of K is equal to ln of A minus EA divided by R multiplied by 1 by T. Or you can write it in the form of logarithmic form as well. You can say log of K is equal to log of A minus EA divided by 2.303 multiplied by R multiplied by T. These are some of the results which you need to remember regarding the Arrhenius equation as well. Or you can convert it into the different result as well. You can write that log of K2 divided by K1 is equal to EA divided by 2.303 R 1 divided by T1 minus 1 divided by 2, something like that. You can get that result from this equation itself, yeah? Right? So these are the results, and this is basically the curve between log K versus 1 by T. Log K versus 1 by T, the curve is going to be a straight line with a negative slope, and the slope of this curve is going to be minus EA divided by 2.303 R, right? So people, with this, your physical chemistry formulas are done and dusted. I'm sure you would have enjoyed the video, and people, at the same time, you'll be getting the PDF of this session in the Telegram group right after this session. So do join the Telegram group as soon as possible, right? Okay? And do not forget to attend the tomorrow session. Do not forget to attend the tomorrow session. I'll be starting the tomorrow session at 9 a.m. in the morning, and the session will go on continuously because we are going to do some 1,000 questions tomorrow, which is going to revise your complete chemistry, and do let your friends also know about it, right? Because it's going to be one interesting session. And I believe out of those questions, 30 to 35 questions of the same type, of the same patterns will be asked in your NEET 2021. I believe that, yeah? Okay, I won't say the questions will come with the same values. It's not the same values, but the types of the questions will be the same, okay? You just remember, your entire chemistry will be done tomorrow, right? And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. And the ones who are NEET 2022, NEET 2023 aspirants, you can join in our plan, our long-term batches, right? Wherein we have got different plans. The link is there in the description box. If you want me to train you, you can use the coupon code, get enrolled and get trained by us particularly, right? Okay. So I'll see you guys tomorrow then. Thank you everyone. Thank you so much. I'll see you guys tomorrow. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye. Ritika, everything will be done. Inorganic, organic, everything. Tomorrow, 22 chapters will be done.